Welcome viewers, in this video we will see the construction of a DC machine. Subscribe the channel for more electrical videos. The soft copy of this material available in the drive. The link is given in the description box. Now we will go to the topic, construction of a DC machine. The DC machine is a device which convert electrical energy into mechanical energy or mechanical energy into electrical energy. So while converting mechanical energy into electrical energy, it is called a DC generator. While converting electrical energy into mechanical energy, called a DC motor. So the same machine can be used as either a generator or motor. So there is no difference in the construction. The same machine is used for generator as well as a motor. So that it is called a DC machine. So the construction will always deal with the DC machine. So that machine can be act as either generator or motor. So the DC machine mainly having two main parts are available, the stationary part and rotating part. The stationary part is nothing but producing the magnetic flux. The stationary part is nothing but the coils are available, windings are available, so that will produce the magnetic flux. The rotating part is nothing but a armature. There also the coils are available. So the conversion of electrical energy to mechanical energy or mechanical energy to electrical energy will be takes place in the armature, right. So we have the detailed diagram available at the time, we can easily understand. So the mainly we have stationary part, that is the coil, it will produce the magnetic flux. Rotating part called the armature, the conversion takes place in the armature. Now we'll go to the detailed diagram. So this is the stationary part. This one is the stationary part called a yoke or frame. Here the coils are available. It's called a field windings. The stationary part, the coil what is available is called a field winding. So the center what we have is the armature, rotating part. So there also coils are available, right. So this is the stationary part and this one rotating part. So in the stationary part, we will see first the yoke or frame is available, outer cover holding all these windings and armature, the outer frame is available. See, this is the pole core. Pole core is nothing but where we are going to place the coils. Here the pole core, this one pole shoe. So this dotted line is nothing but a coils, field coils, right. So this dotted lines, this shaded portion is the field winding. So the field winding is placed in the pole core over the pole shoe. In that the coils are winded. So here the four poles are available. These two pole is the N pole. These two are S pole. So the direction of windings are given such a way that it will produce N pole, this will produce S pole, this will produce N pole and this will produce S pole, right. So this field windings are available in the pole core over the pole shoe. So while the excitation is given, it becomes the magnet, it's called a electromagnet. So the stationary part is the field winding, it will produce the magnetic flux when the excitation is given. The poles are alternatively, N pole and S poles are available alternatively, right. Now center what we have is the armature. What are the parts available? This is the armature core. Armature core means the place to put the windings is called a armature core. So this dots is nothing but a armature winding. So this is a cross sectional view. Normally it is available in a cylindrical form. This armature core, this armature is available in a cylindrical form, right. So this is a cross sectional view. So here the armature core is available, over that armature windings are placed. So this dotted line refers the armature winding, so rotating part. In order to supply the current or taking the current from the armature, what we have, the brush is available. That this is nothing but a brushes. This center portion is nothing but a commutator. This commutator is a device to supply the or take the current from the armature, right. It is a copper coils. This lines, this small line is nothing but the insulation between each and every segment, right. So what we have here, the brush is available, that will use to collect or supply the current. Then this is the shaft, center portion is the shaft, and this is the commutator, right? So what we have, the commutator available at the center with the brushes in order to collect the current or supply the current to the armature, right? So we have stationary part, in that coils are available. When excitation, it becomes the electromagnet. At the center, the armature conductors available, and commutator with the brushes also available, right? So what will happen if it is motor or generator? We'll see that. So if it is motor, what we are, the mechanical energy is the, motor means electrical energy is the input, mechanical energy is the output. So the electrical energy is given to this armature. So the current is flowing through this armature. So it becomes a current carrying conductor. So in a motor, the electrical energy is the input, the mechanical energy is the output. So the supply is given to this armature. So the current is flowing through the armature coil. So it becomes a current carrying coil. Then excitation is given to this field winding, either self excited or separately excited. The topic is separately available. So excitation means to make this field winding into magnet. Now the supply is given to the armature coil, so it becomes a current carrying coil, and field windings are become a magnet. So what will happen if a current carrying conductor placed in a magnetic field, it experiences a force. Experience a force means it will start rotate. So that is a motor. Electrical energy is given, current is flowing through the armature coil. So this current carrying coil placed in the magnetic field, so that it experiences a force, it will start rotate, right? So this is the magnetic field, is a current carrying coil. In case of generator, what is the input? Mechanical energy is the input. That is, we are going to rotate this armature. While rotating, it should produce the electrical energy. So the generator, mechanical energy is the input and electrical energy is the output. What is the mechanical energy? We are rotating this armature by using either another DC motor or prime mover. Prime mover means diesel generator or diesel engine or petrol engine. By using that, this armature is rotated. Now this field windings are excited. It is a magnet. It becomes a magnet. So what will happen in this generator? When a conductor cuts the magnetic field, an EMF is induced in the conductor. So this conductor is now rotating. Mechanical energy is given, rotating. This conductor is rotating in a magnetic field. Whenever the conductor cuts the magnetic field, then EMF is induced in the winding, in the coil. So that EMF is collected through the brushes. Through these brushes, the EMF, the generated voltage is collected, right? So in generator, mechanical energy is given, it start rotating. At that time, the fields are, magnetic field is available. So when a conductor cuts the magnetic field and EMF is induced, that EMF is taken from through this commutator, right? So this is the machine applicable for both motor as well as generator. Based on the input, it will act as either motor or generator, DC motor or DC generator, right? So the base, it is available at the bottom, the base is available. So it will hold the entire portion of the stationary part as well as rotating part. Now we'll go to the description of this one by one. First we will see the yoke or frame. So that is the thing, outermost part of the machine. So it will hold the entire part. So it is made up of cast iron for small machines and cast steel and silicon steel for large machines. So it's the outer cover that will hold the entire part. So it is made up of cast iron in case of small machine, or cast steel or silicon steel in case of large machine. What is the function of this yoke or frame? Act as a protecting cover for the machine. So it will hold all the device, all the material, all the windings, everything, and also to give the protection. It is fully covered. Poles are fixed to the yoke, so it serves as a mechanical support for the part. The poles are available. right, the winding. In order to put the winding, the poles are available. During the construction itself, they will decide the pole. Either it is a 4 pole or 6 pole or 8 pole or 16 pole. Accordingly, the construction is given. Over the pole, we can place the winding. So, it is the function is to hold the winding also. Carries magnetic flux produced by the part. So, the poles available, when the winding is given, during excitation the flux is produced. So, this yoke also carries the magnetic flux. It is part of the flux also produced by, carried by the this yoke. It is a function of this yoke or frame. Next, we will go to the pole core and pole shoe. That is nothing but a field poles. Right. The field pole consists of pole core and pole shoe. First, we will see pole core. So, the pole core may be a solid structure or made of laminations. So, this is the place to place the windings. This is called a pole core. It may be solid structure, but normally it is based on lamination. Like a thin sheets, like a notebook, that the sheets are available. Every sheet is laminated so that we can reduce the losses. So that it is given by lamination. Lamination reduces the eddy current loss. It is made up of cast iron or cast steel lamination, right. The solid structure is applicable for only few machines, but normally it is made up of the lamination. Each and every, it is a thin sheet available, n number of thin sheets are compressed together, but each sheet is laminated with the varnish, so that the eddy current loss will be reduced. So, what is the function? The field winding is wound around the pole core. So, the winding is placed in the core. Core means, pole core means, there is nothing but the place to put the windings, right. So, it will carry the field winding. Then pole shoe. The pole shoe is made up of cast iron or cast steel. What is the function of this pole shoe? Support the field winding. Spread the flux in the air gap. Due to larger cross section area, they reduce the reluctance of the magnetic path. So, it is a place to put the winding. So, it will spread the fluxes in the air gap and also reduce the reluctance of a magnetic path. Now, we will go to the next part. Pole coils are field windings. Now, we discuss pole core and pole shoe. So, these windings are placed in the pole core or pole shoe. So, it is nothing but it is a copper wire wound on a former and placed over the pole. I already discussed, pole is the place to put the windings, right. So, this copper wire is the winded and placed in the pole. The field windings are concealed in series with each other. All the field windings are connected together in opposite direction, so that it will produce N pole and S pole alternatively. It is not connected in a unique direction, unique connection. It is an opposite connection, so that the alternate poles are created. They wound in such a direction around the pole core, so that alternate N and S poles are formed, right. So, the connections are given such a way that it will produce N and S poles alternatively, right. So, the pole core and pole shoe we discuss. In that pole core and pole shoe, we are placing the field winding. What is the function of this field winding? When a current passes through this coil, they magnetize the pole, which produce the required magnetic flux. So, the magnetic flux is produced in the field winding. When the excitation is given, it will produce the magnetic flux, right. Then we will go to the rotating part, armature core. So far what we discuss is the stationary part. So, in the armature core, it is a cylindrical shape. I already informed, cylindrical shape. In the diagram what we seen is a cross sectional and is mounted on the shaft. It is a rotating part. So, it is mounted on the shaft. It is a cylindrical shape. It is made of circular stamping, that is lamination. It is not a single piece, it is a lamination. N number of sheets are available. Each and every sheet is laminated and compressed together. It is made up of silicon steel insulated from each other. So, each and every sheet is insulated, so that we can reduce the losses. The laminated structure reduce the eddy current loss. Eddy current loss we'll see later. So it will reduce the eddy current loss. It has slots on the outer periphery to house the armature winding. The slots called a pole. The slots will be there. Over the slot the armature winding can be placed. It is made of silicon steel to reduce hysteresis losses. Right? So in order to reduce the hysteresis losses, it is made up of silicon steel. So what is the function of this armature core? To have armature winding, to place the armature winding, to rotate the armature winding in the magnetic field, produce very low reluctance path, right? So this armature core is a place to put the armature winding and thereby rotating the armature also. Now we'll go to the next topic. Now we'll see the armature winding. So we discussed armature. In that armature this winding is placed. That is, it is a copper wire wound on a former and placed in the slot. So copper wire is placed in that slot so that it acts as a conductor. So in this winding there are two types available, lap winding and wave winding. There are two types are available. We'll see this one by one. So in this lap winding, the number of parallel path equal to number of pole, that is A equal to P. What is number of parallel path? There are n number of poles available mean n number of parallel path will be there. 4 poles available mean 4 paths will be available. The number of brushes is required to the number of poles. Used for high current, low voltage applications. Normally used for generator of capacity more than 500 amperes. Now we'll see what is this winding, how it is connected. So this is a coil. These coils are available. This is nothing but a commutator. There are n number of segments are available. So in this lap winding, the number of poles equal to number of parallel paths. So 4 poles available, 4 paths will be available. See this first coil is start from here and it is connected to the second segment. First coil starts here. S1 is starts and go with the finishing F1. It is a start and finish. S1 means start, the first starting. F is the first finishing. So it starts at the coil starts at the first slot of the commutator and finish at the second slot of the commutator. The second coil start from second slot of the commutator and then finish at the third slot of the commutator. So like that the windings are placed. So there are n number of windings are available. Number of parallel path equal to number of poles. Like that it is going, lap winding, right? So each and every coil is closed, right? Start, end, like that it will go. Start from 1, end with 2. Start with 2 and end with 3. Like that it will go. Start in one slot, finish in the second slot. Similarly, start in the second slot, finish in the third slot. Like that it will go. We have the one more winding, wave winding. So another type of winding is wave winding. Here number of parallel path equal to 2, irrespective of the number of poles. So only 2 parallel paths are available, right? Start from one point, it will complete all the poles. Number of brushes is always required is only 2. Only 2 brushes are required. Start, end, like that. Used for low current, high voltage applications. Preferred for generator of capacity less than 500 amperes. So the previous one, lap winding, used for more than 500 amperes. This one used for less than 500 amperes. Now we'll see the connection. In wave winding, one end part of coil is allied to the beginning of end part of another coil. So in the previous method, each and every coil having starting and ending. But here, one end of the one coil is the beginning of the another coil. So the same, only one path, only 2 paths available. So we start with one coil, it goes to the beginning of the next coil, has the similar polarity like the first coil. These coils are allied in a wave form and it is called as wave winding. Like a wave, it will go So that it is called a wave winding. We'll see the diagram so that you're able to understand easily. So this is the commutator segments 1, 2, 3. See here, the coil 1 start at the first segment. It will go like this. It will keep on, it is rotate, keep on, it is placed, and end with the, after some places it is end with the finishing S1. Right. So if it is n number of, if 5 poles are available, 5 times it will go and end with 1 point. So starting and ending is S1 and F1 is like a wave, it will goes. But in previous case, each and every coil is completed. Right, start and end with the next slot immediately. Start 1 means it will end with the second slot immediately. Start with the second slot means end with the third slot immediately in the previous case. But here you start here, if 6 poles are available mean 6 times it will go like a wave and finish at the another point. Right. In previous case, 1 pole is completed entirely, then only it will go to the second pole, then third pole. But here all 6 poles are completed in a one like a wave, then it will complete. Right. So that's called a wave winding. Right. I think you were able to understand. Lap winding means each and every pole is completed, then it will go to the next pole. Here all poles are covered by the coil. Right. So these are segments. Now we'll go to the next one, commutator. How this commutator collect the current or supply the current to the armature winding. A commutator converts alternating voltage into direct voltage. It is cylindrical structure. It is built of segments made of hard drawn copper. The segments are separated from each other by microstrip. Is separated by microstrip. These segments are connected to the winding. Right. So we already discussed that. See this diagram. So this is the segment. N number of segments are available. So it's made up of copper and is separated by the mica strip. So there is no connection between these two segments. Right. Segments are made up of copper separated by the microstrip. So it will use to convert alternating to direct current, and one more diagram is available. So I already told it's a cylindrical form. Right. So this is nothing but commutator segment with hard drawn copper to reduce wear and tear. So this is nothing but a copper segments. So these lines is nothing but a mica insulation. Each and every segments are insulated by the mica. There is no connection, there is no short circuit. Right. So that the coil, if suppose if 12 poles are available, mean there will be 12 segments will be available. Each and every pole is supply is given separately from the segment. Right. And also it is insulated by the mica insulation. Now we'll see what is the function of this commutator. The commutator function is collect the current from the armature winding, convert the alternating current into unidirectional current. It produces unidirectional torque in the motor. Right. So it will collect the current, also supply the current. In case of motor, it will supply the current. In case of generator, it will collect the current and also convert into unidirectional current. Right. So the commutator is the important part to collect or supply the current to the armature. Now we'll see the another next topic, brush gear. To collect the current from the commutator and give it to the load. So the brushes are available, copper brushes. Right. The brush gear consists of brushes and brush holder. Because it's rotating part, the brush is available, so it will continuously collect the current from the commutator, that is from the copper segment. So what is brush? The brush are stationary and rest on the surface of the commutator. It is made up of copper, graphite or carbon because it is continuously rotating. So wear and tear will be available. So it is made up of either copper, graphite or carbon. What is brush holder? The brush holder hold the position by means of the brushes are hold in position by means of brush holders. These brushes are held by these brush holders, right? So the commutator is the place to supply the current or take the current from the armature. That is done through these brushes. The current is taken or given by the brushes. So finally what we have, the shaft. So all rotating parts are mounted on the shaft, that is armature winding, brush, everything are mounted. So it is a rotating part. So in this video we discuss about the construction of a machine, DC machine. That is the same machine used as either generator or motor. Accordingly, what are the parts available we discussed, stationary part and this rotating part. Subscribe this channel for more videos. The material is available in the link. The link is given in the description box. The other topics of the DC machine available in the also available in the description box. Thank you. Welcome viewers. In this video we will see the principle of operation of a DC generator. Subscribe the channel for more electrical videos. The link is available in the description box. Soft copy of this material is available in the drive. The link is given in the description box. Now we'll go to the topic. So the principle of operation of a DC generator, it is working on the principle of Faraday's law of electromagnetic induction, based on the Faraday's law. The Faraday's law states that whenever a conductor cuts the magnetic lines of force, an EMF is induced. So the conductor will cut the magnetic lines of force, then EMF will be generated. So we need to see what is the conductor and how the magnetic field is produced. The conductor is nothing but a armature. The armature is the rotating part, in that the conductor available. The magnetic field is produced by the field winding, stationary part, so that EMF is generated. When the armature rotates in the magnetic field, EMF is generated. The detailed diagram available at that time, you are able to understand easily. The direction of the induced EMF is given by Fleming's right hand rule. Fleming right hand rule will give the direction of induced EMF. Fleming left hand rule give the motor based on the DC motor. For generator it is applicable by Fleming's right hand rule. Now we'll see the operation one by one. When DC supply is given to the field winding, the magnetic poles will get magnetized and produce the flux. That flux passes through the north pole to south pole through the air gap. So the first step, we are giving the DC supply excitation to the field winding, so that these magnetic poles are magnetized and it will produce the flux that is passing from south pole to north pole through the air gap. So stationary part, field winding, the field windings are magnetized. Now the rotating part, the armature is rotated by means of prime mover in the magnetic field, because generator is a mechanical energy, is the input. There is a rotation that is given by the prime mover. So by using prime mover, the armature is rotated, mechanical energy is given, so that the armature conductor cut the flux. The flux already produced by field winding is cut by this armature conductor. Therefore the flux linking the conductor changes and EMF is induced in the armature winding. Then EMF is according to the Faraday's law of electromagnetic induction. Right? The armature is rotated, already magnetic field is available. So this armature conductor cut the magnetic flux. Due to rate of change of flux, EMF is induced based on the Faraday's law of electromagnetic induction. The EMF induced in the armature is alternating. By the use of commutator, the alternating voltage is converted into direct voltage. The direct voltage is taken to the electrical circuit through the brushes. I will see the diagram, at the time you are able to understand. So the commutator used to collect the current, also convert into direct current, right? It is collected through the brushes. Now we will see the operation. The essential part of generator is conductor and magnetic field. The conductor is nothing but armature, rotating part. Magnetic field available as a stationary part, or field winding. So based on that we can go for the operation. When the conductor move in the magnetic field, it cuts the magnetic lines of force and EMF is induced. This conductor nothing but armature. When the armature is rotating in a magnetic field, it cuts the flux, it cuts the magnetic lines of force and EMF is induced. For understanding purpose, let us consider a single turn of rectangular coil ABCDA placed in the magnetic field produced by permanent magnet or electromagnet. Right? For understanding purpose, we consider rectangular coil with ABCDA with a single turn. Normally it is a circular form, but for understanding purpose we consider rectangular coil. The coil side AB, is connected to the slip ring S1 and CD is connected to the slip ring S2. AB is connected to S1, CD is connected to S2. The brushes B1 collect the current from AB through S1 and give to the external load circuit ML, right? So AB is connected to the brush S1, connected to the slip ring S1. The brush B1 is collecting the current and is giving to the external load of ML. So AB S1, brush is B1 and the load circuit is ML. Similarly, brush B2 collect from CD through the S2 slip ring and giving the external circuit ML. The coil is rotated in anti-clockwise direction in the magnetic field. As the coil takes different position in the magnetic field, the flux linking and also changes, hence the magnitude of EMF also changes. So we are rotating the coil so that different position will be available. So due to the different position, the fluxes are changes, rate of change of flux also there, so that the EMF also changes. So the brush B1 is connected to terminal M and brush B2 is connected to the terminal L, right? So here, so the brush B1 collect the current from AB through the slip ring S1 and give it to the external circuit ML. Similarly, CD through the S2 and connect to the load circuit ML. Now we'll go to the detailed diagram. So first we will consider the position 1, that is 0 degree. We will go to the entire circle 0 degree, 90, 180, 270, again 0 degree. 4 positions available. So we start with the 0 degree, right? Position 1 at the 0 degree. Now we consider the rectangular coil for understanding purpose. A, B, C, D, A, rectangular coil. So this is nothing but a magnet, either permanent magnet or electromagnet. This is called a field windings. These two are field winding. One is N pole and another one is S pole. So it is named as A, B, C and D. Right? So here we have the two slip ring S1 and S2. The brush B1 collect the current from slip ring S1. Brush B2 collect the current from S2. So the 4 position available 1, 2, 3, 4. The position 1 is the 0 degree, right? It is vertically available. The rectangular is vertically available. Position 2 90 degree. Position 3 again 180 degree, again vertical. Position 4 270 degree, right? So let us assume that this rectangular coil is placed vertically so that the space covered between N and N pole will be very less, right? If it is placed horizontally, so the entire space is occupied by this rectangular coil. Now if it is placed in the vertical, means only less amount of space will be covered by the rectangular coil, right? So due to that, what will happen? The flux coming from N pole is easily passed to the S pole, right? The fluxes are moving from N pole to S pole easily. The area covered by the coil is very less. So what is another term? Rate of change of flux is very less. All the fluxes from N pole easily goes to the S pole, right? There is no rate of change of flux. But based on the Faraday's law, the important thing is the EMF is induced when there is a rate of change of flux. But in this position, due to the coil is placed in a vertical manner, all the fluxes from N pole is linked with the S pole. The rate of change of flux is very less. So the EMF induced also very less in this position. Now we'll see the description. When the coil is at position 1, flux linking the coil is maximum. That is, the flux from N pole is easily linked with the S pole, because the area occupied by the coil is very less, but the rate of change of flux is very less. That is, d pi by dt is minimum. The flux linkage is maximum, but the rate of change of flux is minimum. d pi by dt is minimum. So at position 1, the flux linkage is maximum, but rate of change of flux d pi by dt is minimum. So that EMF is purely based on d pi by dt. d pi by dt is minimum, so EMF also minimum. That is almost 0. At position 0, the EMF induced is 0. Right? Now we will go to the next position. So the second position is 90 degree. The coil is rotated anti-clockwise by 90 degree. So that, see this, it is horizontally available. The coil is horizontally placed. So the area covered by the coil is more. In between N and S pole, the almost the area is covered by this coil. In previous case, it is placed in a vertical manner, so that the area covered is less. So the flux linking from N coil to S coil is very minimum. That is, rate of change of flux is maximum. Right? Because the EMF induced purely based on rate of change of flux. So the flux from N pole is not easily linked with the S pole. The rate of change of flux is more, because the area is covered by this coil. Right? So that is given. The coil is rotated in anti-clockwise by an angle 90 degree, so that it is placed in a horizontal manner. In this position, the flux linking the coil is minimum, but rate of change of flux is maximum. Right? Only the few flux will link, but the rate of change of flux will be more. Right? So based on that, flux linkage is minimum, but rate of change of flux is maximum. So the EMF is based on the rate of change of flux, so the EMF also maximum. Right? At 0 degree, the flux is 0. At 90 degree, the flux is maximum. So in between 0 to 90 degree, it is slowly increasing from 0 and reaches the maximum value at 90 degree. Right? So in this position, the current flows downward in the conductor AB and current flows upward in the conductor CD. Now we will go to the third position. So third position, 180 degree. Again the coil is rotated by anti-clockwise direction by 90 degree. So that again it will come in a vertical manner, but the directions are different, A, B, C, D. Earlier in position 1, the A, B, C, D like this. Here the A is available, now the A is rotated to this position. So it is very similar to the position 1, but only the current direction is different. Right? So the area covered is very less, vertical. It is placed in a vertical. So many areas are available. So the flux from N pole is easily linked with the S pole. So the rate of change of flux is minimum. If the rate of change of flux is minimum, means the EMF induced also minimum, it is almost 0. So in the previous position, the EMF induced is maximum, here minimum. So in between this 90 degree to 180 degree, it is decreasing from maximum to 0. Right? So the details are given. The coil is rotated again by an angle 90 degree. The flux linkage is maximum, but rate of change of flux is minimum, so that the EMF induced also minimum. Right? So it is decreasing from maximum to minimum in this position. From second position to third position, the EMF induced is decreasing from maximum to minimum. Now we will go to the fourth position. So in the fourth position, again it is rotated anti-clockwise by 90 degree. So again the coil is placed in a horizontal manner, very similar to the second position, but the direction is different, A, B, C, D. Earlier A, B, C, D like this, now it is rotated. So again in this position, the flux linkage is very less. So the rate of change of flux is more. The flux not easily link from N pole to S pole because area is covered by the coil, so that the rate of change of flux is maximum. Is given here. In this position, flux linkage of the coil is minimum, but the rate of change of flux is maximum, so that EMF induced also maximum. So in the previous case, EMF induced is 0, now it is maximum, right? So it means that from 0 it is slowly increasing and reaches the maximum value. Now we will see the further details. The direction of induced EMF is given by Fleming's right hand rule. The current flows downward in the conductor CD and upward in the conductor AB. So that is clearly given in the diagram. The direction of current is DCLMBA, right? Now we will see the diagram so that you can easily understand. So this is the induced EMF. So positions are given 1, 2, 3, 4, again 1. So in the position 1, the EMF induced is 0. In position 2, maximum. So in between 1 and 2, it is slowly increasing. So while rotating the coil from 0 degree to 90 degree, the EMF also increases. At 90 degree, it is maximum. Again, while moving from 90 degree to 180 degree, it is decreasing from maximum to 0 and reaches the 0 value at this 180 degree. Again, it is rotating in a reverse direction. From 180 to 270, it is 0 to maximum. From position 4 to position 1, again it is decreasing. It reaches the 0 value, right? So it keep on changes 0, maximum, then 0, again maximum and 0. But the current direction is reverse because the conductors are moving in anti-clockwise direction. So the current will flow A to B or B to A, upward or downward, accordingly it will change. But here we are discussing the DC generator. This is the alternating current, AC. So that AC can be converted into DC, unidirectional DC, like this 1, 2, 3, 4. So that is done by, so the alternating output is converted to unidirectional output or DC output by replacing the slip ring. Slip ring means it keep on changing the position, right? The current will flow A to B, after that the current will flow B to A, slip. It is the meaning slip is keep on changes, but while using the commutator segments or split ring, right? This the output is replacing the slip ring by commutator segment or a split ring. Split ring means when the conductor position changes, it will change, it will not change the direction, right? So always it will flow like this in a unidirectional. So by using the split ring, we can convert the alternating current into direct current, right? So in this video, we discussed the operation of a DC generator, how the EMFs are induced. So from 0 degree, 90 degree, 180 degree, 270 degree, again 0 degree. 0 degree minimum, 90 degree maximum. That means slowly increasing from 0 to maximum, 90 degree. 180 degree again minimum, decreasing from maximum to minimum. Again in 270 degree it is maximum, right? It is slowly increasing. So that same thing repeats, right? Subscribe this channel for more videos. The soft copy available in the drive, link is given in the description box. There are other video links also available in the description box. Thank you. Welcome viewers. In this video, we will see the generated EMF, that is the EMF equation of a DC generator. Subscribe this channel for more electrical videos and notification. The soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic, EMF equation of a generator. First we'll see the what are the parameters available. The pi is the flux per pole. The unit is Weber. Flux per pole. The Z is nothing but total number of armature conductors. So that is nothing but number of slots into number of conductors per slot, right? So this number of conductor per slot multiplied by number of conductors will give the total conductors in a armature conductor. P is the number of generator poles. So during the manufacturing itself, this number of poles will be decided. A is the number of parallel path available in the armature. This parallel path depends upon the winding, either wave winding or lap winding. Based on that, we can decide the number of parallel path. N is the armature rotation in revolution per minute, RPS. The speed of the DC generator is given by N, armature rotation, that is the unit is revolution per minute. So the E is the EMF induced in any parallel path in a armature. So the EMF is given for a parallel path in a armature. So these are all the various notations available. Now we'll go to the EMF generation. So the generated EMF equal to EMF generated in any one of the parallel path. So now we consider the parallel path first. The EMF generated in parallel path. The average EMF generated per conductor is nothing but d pi by dt. The average generated is d pi by rate of change of flux. There we consider n equal to 1. Normally it is n d pi by dt. Here we consider n equal to 1. So d pi by dt. Now we'll find what is the value of d pi and what is the value of dt. What is the flux available, rate of change of flux, and what is the time taken. So that if you find these two parameters, we can easily identify the EMF generated, average EMF generated. Now flux cut per conductor in one revolution. So there is a rate of change of flux, then only the EMF will be induced. So what is the flux cut? Flux rate of change of flux is d pi equal to pi into p. The flux available and number of poles available in the generator. So pi into p will give the how much of flux cut per conductor in one revolution. So that it is pi into p Weber. The number of revolution per second equal to n divided by 60. This n is the number of revolution per minute. In order to convert into second, it is divided by 60. So the time taken for one revolution is dt equal to 60 divided by n seconds. So the number of time taken is 60 by n. So within a one revolution there are 60 by n seconds. It will take the time of 60 by n seconds. Now we got the value of d pi as well as dt. So d pi by dt will give the generated EMF. So according to the Faraday's law of electromagnetic induction, EMF generated per conductor equal to d pi by dt. The d pi what we calculated is pi into p, flux into pole, divided by the time taken 60 by n. So this n will go to the numerator. So pi p n divided by 60 voltage. So the generated EMF equal to pi p n divided by 60 voltage. So this EMF depends upon what is the flux available in the generator, number of poles, then speed of the generator divided by 60. Now we'll go to the parallel path. So this is for EMF generated per conductor. Now we'll go for EMF generated per path. That is based on the winding, type of winding, either wave winding or lap winding. Now we'll see this one by one. First consider a simplex wave winding generator. The winding type is wave winding. So in case of wave winding, the number of parallel path equal to 2. Always for wave winding, the number of parallel path will be 2. So that number of conductor in one path is Z divided by 2. That is connected in series. So only two parallel paths available. So number of conductor in a path is Z divided by 2. So EMF generated per path is nothing but pi Pn divided by 60 into Z by 2. So earlier we calculated EMF generated per conductor. Suppose if you want to find EMF generated per path means, so this value is the EMF generated per conductor. Within that we are multiplying the number of conductor in one path. So pi p n divided by 60 into Z by 2. So that it is nothing but pi n p pi Z p n divided by 120 voltage. This is for a wave winded generator. Pi Z p n divided by 120. Now we'll go to the lap winding. In case of lap winding, the number of parallel path equal to number of poles. Number of parallel path equal to p. How many poles are available, that much number of parallel path will be available. So the number of conductor in series in one path is Z by p. In previous case we taken Z by 2. Now it is Z by p. The number of parallel path is equal to number of poles. So that EMF generated per path is pi p N divided by 60 into Z by P. Right. So this is the EMF generated per conductor. So this is the EMF generated per path by multiplying number of conductors. Right. So this the P got cancelled, number of poles got cancelled. So pi Z N divided by 60 voltage. So this expression is applicable for wave lap winding. Right. So in general, either lap winding or wave winding, generally one equation is available. Eg equal to pi N Z divided by 60 into P by A voltage. Right. So here this P, the A, number of path. In case of simplex wave winding, A equal to 2. We can substitute A equal to 2, always it is 2. In case of lap winding, A is nothing but number of poles. So that A equal to 2 for wave winding, A equal to P, number of poles in case of wave winding, in case of lap winding. So we can use this. This is the general equation for EMF generated for both lap winding or wave winding. Accordingly, we can substitute the number of parallel path. So pi N Z divided by 60 into P by A voltage. So this is a general equation. It is applicable for both wave winding as well as lap winding. Then we'll go with the angular velocity. The same, the EMF generated EMF is expressed in terms of a angular velocity. For that, this 2 pi is multiplied and divided. So already we have this N by 60 is already available, pi Z P by A is available. So in order to get the angular velocity omega, omega is nothing but 2 pi N divided by 60. In order to bring this order, we are multiply by 2 pi and divide by 2 pi, so that the originality will not change. So the remaining terms are as it is available, pi Z P by A all are available. So this 2 pi N can be replaced by omega, that is nothing but angular velocity. 2 pi N divided by 60 is nothing but a angular velocity. Then remaining terms are available, this 2 pi available, this pi Z P by A. So this equation is also the generated EMF in a DC generator. It is given in terms of velocity. In a problem, or if while solving the problem, if a angular velocity is available, we can use this formula, omega pi Z divided by 2 pi into P by A. Right. So this is the general equation for either lap winding or wave winding. We can use this. So this equation applicable when the angular velocity is given. So in this video, we discuss the generated EMF of a DC generator for both lap winding as well as wave winding, and also one more expression for including the angular velocity. So subscribe this channel for more videos related to the electrical topic, and soft copy of this material is available in the drive. The drive link is given in the description box. Thank you. Welcome viewers. In this video, we will see the types of a DC generator. Subscribe the channel for more videos. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. So the types of the DC generator. So based on the excitation of DC generator are classified as follows. The classification is based on the excitation given to the DC generator. Excitation means the supply given to the field winding in order to make it as a magnetic field. So in that there are two types available, separately excited or self-excited. So primarily two types. The excitation is given separately to the field winding in order to make it to as a magnet flux, in order to produce the flux, or self-excited. These field windings are connected with the armature. So by self itself it will produce the magnet by using the concept called residual magnetism. Right. So based on the excitation, the generators are classified. The major classification is separately excited or self-excited. Excited means giving the supply to the field winding in order to make the magnetic field, so that produce the flux. So that we have separately excited, separate DC supply is given to the field winding for excitation. Here the field winding is connected in series with the armature, So the self itself, it will produce the magnetism, right. So the separately excited, self-excited. The self-excited, again it is classified into three different type. That is the armature winding and field winding, how it is connected. So it is connected in series, mean it is series generated, armature winding and field winding. If it is connected in parallel, means shunt generated. Both both having shunt winding as well as series winding, means it is compound generator, right? The field winding is connected series here, field winding is connected in parallel here. Here both connected in series as well as parallel. So that is called a compound winding, combination of both series and parallel. This compound generator, again it is classified into two different type. Long shunt compound generator, short shunt compound generator. Short shunt means the shunt winding is connected immediately to the armature, thereby series winding is connected. Long shunt generator means the series winding is connected immediately to the armature. The entire circuit is connected in series with the shunt winding, shunt field. So that is called a long shunt or short shunt. The detailed diagram is available at the time, we are able to understand easily. Right. So in this short shunt and long shunt, we have the series field winding as well as shunt field winding. Two windings are available in both the type. So due to the two winding, again it is classified into two different type, cumulative compound or differential compound. If series winding and field windings are added together, then it is called a cumulative compound. If it is opposing each other, then it is called a differential compound. That is applicable for this type also, short shunt compound generator, right? So this is the classification. We will see this classification, we will see the types one by one. So first we will see the separately excited DC generator. The generator where field winding is excited or energized by external DC source is called a separately excited DC generator. The excitation is given separately. Now we will see the diagram. So this is the armature winding, rotating part, armature winding. This is the field winding, stationary part, right? So the generator, so it will generate the power, the energy that is available in the load end. So for this field winding, it is given, the excitation given separately by the another DC source through this rheostat. In order to control the voltage applied to the field winding, this rheostat is used, right? So the DC supply is given while adjusting the rheostat. This winding become, field winding become, current will flow, then magnetic field will be created, right? So this excitation is given separately. This is the field winding, this is the armature winding, right? So due to this interaction between this armature and field winding, the EMF is generated. EMF is generated in the armature. So that is available at the load terminal, right? So this is the field winding RF, is the field current, rheostat and DC source. This RA is the armature resistor. Current flowing from the armature is the armature current, IA. While going to the load end, it is IL. Right. So this EG is the EMF generated inside the armature, but while going to the load terminal, some drops will be there. So that is nothing but this, the armature resistance drop, IARA, and as well as load voltage, right? The EMF generated from that, this armature resistance drop is subtracted, the balance will be available at the load end, right? So these details are given here. So the IL is the load current, IA is the armature current, IF is the field current, RA armature resistance, IF RF field resistance, EG generated EMF. Now we will see the equations. So the output power is nothing but V into IL, the load voltage and load current, V into IL. So in this case, this IA and IL both are equal. The current from the armature is equal to load current, both are equal. So by applying the KVL, the EG, this is the voltage rise, this is voltage drop. So the EG is nothing but IA minus EG minus IARA minus V equal to 0, or otherwise the generated voltage E equal to the voltage available at the load terminal plus the armature resistive drop IA into RA, right? So the generated EMF is the sum of the voltage will be dropped across IaRa, the remaining available at the load terminal. So the sum of these two is nothing but generated EMF, Eg equal to V plus IaRa. So there is small drop in the armature circuit, that is called IaRa. So the power developed in the armature is Eg into Ia, generated EMF into Ia. But while going to the load end, it is V into IL. Some voltage will be dropped here, so some of the power will be reduced. The balance power available at the load end, right? So this is inside the armature. This is outside the armature, that is the load terminal. Eg into Ia is, while going to load end, it is V into IL, right? So there is a small drop called Ia and Ra. Right? Now we'll go to the second type. So self-excited DC generator. So previous one separately, the separately excitation given. Now it is self-excited, that is a DC generator where field windings are excited by the current supplied by the generator itself, are called as self-excited DC generator, right? The current from the field winding, the generator where the field windings are excited from the generator, the current supplied by the generator itself is called a self-excited. There is no external circuit is required. How it is possible? This is due to the property residual magnetism. What is residual magnetism? Where some flux is always present in the pole of the machine. Even after the removal of the supply, some of the flux will be always available in the winding, that is called a residual magnetism. Now we will see the residual magnetism in detail. The property of the magnetic material to retain the magnetic property even after the removal of magnetizing current is called a residual magnetism, right? So after removing the supply, some of the flux will be there, some of the magnetic force is available, that is called a residual magnetism, right? In such machine, the field windings are interconnected with the armature winding, right? The field winding and armature windings are interconnected. The field coil may be either in series or in parallel, or both in series as well as parallel with the armature winding, right? So this armature and fields are connected in a three different way, either in series or parallel or both series as well as parallel, right? So that due to residual magnetism, the field windings are become the magnet, and also this armature winding field winding is connected. So the current generated from the armature is passing through the field winding also. So based on that, it is classified as shunt generator if it is connected in parallel, field winding and armature winding. Series generator, both field winding and armature windings are connected in series. This compound generator, both connected in series as well as parallel. Now we will see these types one by one. So in the shunt generator, the generator in which the field winding is connected in parallel with the armature winding. If field winding and armature windings are connected in parallel, then it is called a shunt generator. Now we will see the diagram. So this is the armature, rotating part. So this is nothing but a brush. This is a field winding. Now both are connected in parallel, right? So the current generated from the armature is used to excite the field winding also. So that it is called a self-excited. Now this is the load end. Armature as well as field are connected in parallel. So that called a shunt generator. Now we'll see this. So the generator EMF will be generated inside the armature. It's called Eg. This Ra is nothing but a armature resistance. So the EMF generated, so the sum of the value will be dropped across this armature resistor in the Ra. The balance will drop across, balance will go to the voltage, the load terminal voltage, and also some of the voltage will drop across this shunt field winding also, right? Now we'll see the term. So this is the EMF generated inside the armature, armature resistance. Then we have this Ia. So here the Ia will come. So that Ia will be splitted, ISH and IL, load current and shunt field current. So based on that, we will see the equation. The output power is nothing but V into IL. terminal voltage into load current. But what is the power generated in the armature? Eg into Ia. Eg into Ia is the power generated in the armature. After the drop, the balance will be available in the load terminal, right? So it is very, you need to clearly, we need to explain. The voltage V is the voltage available in the load terminal. Eg is the voltage generated in the armature, right? So both are not equal. This Eg, there is some drop will be there, balance will be available as a load terminal voltage, right? So that we'll see this equation. Here Ia equal to IL plus ISH. The armature current flowing from the armature is splitted into ISH and IL. So ISH, the current flowing through the shunt field winding is nothing but V divided by RSH, because the voltage across this RSH is nothing but voltage across the load terminal. Both all are connected in parallel, right? So what is the equation, the KVL? Eg minus IaRa minus V equal to 0. So this is the voltage rise. These two are voltage drop. Or otherwise bring these two term in the left hand side, so that right hand side, so that Eg equal to V plus IaRa. The EMF generated inside the armature is equal to the terminal voltage plus the drop Ia into Ra, right? So that these two are not equal. Sum of the voltage is dropped across the armature. Balance is available as a load terminal, right? So this is a very important equation. Eg equal to V plus Ia Ra. Generated voltage equal to terminal voltage plus the resistive drop, armature resistance drop, Ia Ra. Now we will see the further detail. So Ia equal to IL plus ISH. So for effective power to the load current IL should be very high, right? If the load current IL is very high, means the power will be more, so that ISH should be very small. The current diverted through the shunt field winding should be lesser, so that IL will be more. So the ISH is made to high resistance, so that less amount of current will flow. The high resistance mean it is made up of many turns of thin wire, so many turns available, so that only less amount of current will flow through the shunt field winding. That is, the shunt field winding, the current is very less, so that the resistance were increased, so it is made up of many turns, right? So if ISH is very small, mean the IL will be more. If IL will be more, mean more power will be delivered to the load circuit. Now we'll go to the second type. Second type is the series generator. Series generator means the field winding is connected in series with the armature winding. Field winding and armature windings are connected in series. Now we'll see the diagram. So this is the armature winding, rotating part. This is a field winding, stationary part. Both are connected in series. In previous type it is connected parallel. Now it is connected in series. So what will happen here? The current flowing from the field winding, the current flowing from the armature winding, Ia is equal to ISH, current flowing through the series field winding, and also it is equal to the load current. So the only one current is available. This armature current flowing through the series winding, load current, all are equal. That is given here. Ia equal to ISH that is equal to IL, right? So this generated EMF is Eg, right? The generated EMF will be Eg. So that some of the voltage will be dropped across armature resistance and also dropped across series field resistance. Balance will be available at the load terminal. So that is very important. The voltage generated inside the armature Eg, after the balance, after the drop across armature resistance and series field resistance, balance will be available at the load terminal, right? So that is given here. EgIa equal to EgIsc plus Eg into IL. All are same because current is equal. What is the equation, voltage equation? Eg minus IaRa minus Isc Rsc minus V equal to 0. So this is a voltage rise, voltage generated. These are all drops. Drop across armature resistance, drop across the series field resistance, drop across the load terminal. So it can be written as Eg equal to V plus IaRa plus Isc into Rac. That is Eg equal to V plus Ia into Ra plus Rac, right? Because Ia equal to Isc. So the generated voltage is equal to terminal voltage plus drop across the armature as well as the field, right? Some of the voltage will be dropped, balance will be available as the load terminal, available at the load terminal, right? So the remaining term is the output power if you consider V into IL, the terminal voltage into load current, right? Now we'll see the further detail. Since the series winding carries full load current, the value of RSE should be less. RSE is designed with a few turns of thick wire, right? The RSE, because if the RSE is lesser, then only the full amount of current will flow, right? If the RSE is very large, means the current will lesser. But here all are connected in series, so we need to increase the current flowing through armature as well as field winding as well as load, so that RSE should be lesser, right? So RSE is designed as lesser, so that very few turns available with a thick wire. In previous case it is opposite. So many turns are available with a thick wire. RSE is more, right? Because it is diverted, it is connected in parallel. Now it is connected in series. We need to increase the current so that RSE is kept to very minimum value, so that very few turns with thick wire is available. Now we'll go to the third type. The third type is a compound generator. That is, it is a generator in which few turns of field windings are connected in series, few turns of winding is connected in parallel with the armature winding. So both series as well as shunt, series as well as parallel is connected. The field windings are connected series as well as parallel, both are available. So that is called a compound generator. In the first type only shunt winding connected in parallel. In second type only connected in series. In the third type both connected in series as well as parallel. So based on that it is two type, long shunt and short shunt, right? The shunt winding is available after the series. Here short shunt mean the short winding is available immediately, after that series winding will be available. We will see the diagram so that you are able to understand. So due to the two winding, again it is classified into cumulative compound or and differential compound. Whether the two windings are added together means cumulative compound. Two windings are opposing each other means differential compound. Now we will see the diagram. What is cumulative compound and differential compound? See, this is the two windings. This is a series field and shunt field. The compound generator, we have both series winding as well as shunt winding. Is connected in series as well as parallel. See the current direction, both are equal. The current enters here and leaves here. Here also current enters here, leaves here, right? So that the magnetic pole, magnetic flux will be same in both the series winding as well as parallel winding. So it is a cumulative, both will be added together. That is given here. If the flux produced in the series field winding and shunt field winding tends to aid or support each other, it is said to be a cumulative compound generator, right? So because of same current direction, both the flux will be added together. So that is called a cumulative compound. In case of differential compound, see the current direction, current enters in the top coil, but here current enters in the bottom coil. So both the current directions are opposite to each other. So for example, here N pole created means here S pole will be created. So both will oppose each other. So that is called a differential compound generator. The current directions are not equal, both are opposite to each other. That is, if the flux produced in the series field winding and shunt field winding tends to oppose each other, then it is said to be a differential compound generator, right? Here current directions are opposite and flux also opposite, so that called a differential compound generator. Now we will go to the long shunt and short shunt. So long shunt compound generator means the generator in which the shunt field winding is connected in parallel across the series combination of series field winding as well as armature winding, right? The shunt winding is connected across these two windings, so that is called a long shunt. We will see the diagram so it is easier to understand. So this armature winding is available, immediately the series winding is connected. Across these two field winding is connected, shunt field winding is connected, so that it is a long shunt. The series winding is coming immediately, shunt winding is coming afterwards, so that is called a long shunt. right? This long shunt mean the shunt winding is connected across the combination of series winding as well as armature winding, right? Now we'll see the diagram. So this is the generated EMF, EG. This is the load terminal voltage. So after the drop, the balance voltage will be available at the load terminal. What are the drops available? This RA, armature resistance, armature resistive drop. Then this shunt, then series field is available, and shunt field also available, right? So what about the current? Here IA, the current coming out of the armature winding is IA, while flowing through the series circuit is ISC. So both are equal, IA and ISC are equal. Armature current as well as series field current are equal. So at this point it is splitted, load current and shunt field current, ISH and IL, right? So IA equal to ISC, that is equal to sum of IL plus ISH, right? So we'll see the drop, what are the drops available. So the output power will be V into IL, load terminal voltage and load current, right? So the power generated inside the armature is EG into IA. After the drop, the balance will be available here. So what are the drops here? IA equal to ISC. The armature current and series field current is equal. Similarly, IA equal to IL plus ISH. IA is split into load current into ISH. So ISH can be written as V divided by RSH, because RSH is connected across the load terminal, right? So that the same voltage will be applied across RSH also. So the current through the shunt field winding is V divided by RSH. Right. Now we'll see the voltage equation. So EG minus IARA minus ISC RSC minus V equal to 0. Right. So this is the generated EMF. That is converted into sum of the voltage is dropped across armature resistance, sum of the voltage drop across series field winding, sum of the voltage drop across the load terminal, or otherwise you can write it as EG equal to V plus IARA plus IARSC, right? So the terminal voltage, the generated voltage equal to terminal voltage after this drop. The balance, after the drop, balance voltage is V, right? So it can be written as IA, because this ISC both are, this ISC is equal to IA, so that we can write IA into RA plus RSC. So the generated voltage is dropped across the load terminal after this drop across armature as well as series field resistance. Now we'll go to the short shunt. Short shunt generator. See here, this is the armature rotating part. Immediately the field winding is connected, so that is called a short shunt. After that only series winding is connected, right? Immediately the shunt field winding is connected, so that is called a short shunt. After this only the series field winding is connected, so that is called a short shunt, right? So what are the terminal, what are the parameters available? This EG is the generated voltage, V is the voltage available at the load terminal. After the drop, the remaining voltage will be available at the load terminal. So this RA is the armature resistance. This IA is the current flowing from the armature. At this point, what will happen? Both will be splitted into ISH and ISC, shunt field current and series field current. This armature current is splitted into the shunt field current and series field current. This series field current is equal to load current also. Both are connected in series. So ISC equal to IL, right? Now what are the drops available here? We'll see this diagram. EG minus IA RA minus ISC RSC minus V equal to 0, right? The generated voltage from that armature resistance drop is subtracted, series field resistance is subtracted, then load voltage, that is equal to 0, or otherwise EG equal to V plus IARA plus ISC RSC. The generated voltage is not fully available as a load terminal. Some of the voltage will be dropped across the armature resistance, some of the voltage will drop across the series field resistance. This after this drop, remaining will be available as a load terminal, right? So the other terms are output power equal to V into IL. power generated inside is Eg into Ia. So we already discussed Ia equal to Is plus Ish is splitted, but Isc equal to IL, right? So Ia equal to IL plus Ish. So the Ish can be calculated as Vsh divided by Rsh, right? So the remaining voltage after the drop, the remaining voltage available at the load terminal. So coming under short shunt generator. So in this video we discuss about the various types of DC generator, that is separately excited, self excited, again shunt generator, series generator, compound generator. Again it is split into short shunt, long shunt, then further classification, differential compound and cumulative compound, right? So subscribe this channel for more videos. The link is available in the description box. The material link also available in the description box. Thank you. Welcome viewers. In this video we will see the losses and efficiency of a DC generator. Subscribe this channel for more videos. The soft copy of this material available in the drive. The link is given in the description box. Now we will go to the topic. So first we will see the efficiency. The efficiency of DC machine is the ratio of the output to the input. So the DC machine is nothing but it can be act as either generator or motor. Both are same. Construction wise there is no difference. So that is given as a DC machine. So the efficiency is nothing but output power divided by the input power. What is the power we are getting and what is the power given to the machine? So that ratio will give the efficiency. The whole amount of input energy to the DC machine is not available at the output. The input what is given to the DC machine not available at the output. Why? Because of various losses takes place in the machine during the process of electromechanical energy conversion, right? The input given is not exactly available at the output. In between some losses will occur, right? So that we can write input equal to output plus losses. The input what we are giving, so it is converted into output plus some of the losses. By adding the output and losses we will get the input. So what are the losses available in the DC machines? One is the copper loss, because we are having the windings, copper windings are available. So the losses takes place in the copper coil, and we have the core is available, magnetic core is there. So the loss available in the core is nothing but a iron loss or core loss or magnetic loss, right? The core is there and winding is there. The loss available in the winding is a copper loss. Loss available in the core is nothing but a core loss or iron loss or magnetic loss. Then we have mechanical losses also available. Due to friction and vintage, some losses will occur, that is called a mechanical loss. Now we will go to the copper loss. So the copper loss means loss happened due to the copper coil. The loss takes place due to the current flowing through the winding is called a copper loss. The winding is available in the three different places, either armature copper loss. The winding is available in the armature and as well as field. The winding is available both in armature as well as field. So the loss occur in the armature is called a armature copper loss, Ia square into Ra. The loss available in the shunt field copper is nothing but shunt field copper loss, Ish square into Rsh. The loss in the series field is called a series field copper loss, Isc into Rs, Isc square into Rs, right? So the copper available in both rotating part as well as stationary part, so that it is called a three different type, either armature copper loss or shunt field copper loss or series field copper loss. Then we will go to the iron loss. So the iron loss is due to the loss in the core. These losses include hysteresis losses and eddy current loss. There are due to the rotation of the iron core of the armature in the magnetic flux of the field pole. These losses are almost constant. The previous losses, this copper loss, when the current increases, the losses also increases. If the armature current increases, the losses will increase. So this depends upon the current. So that it is a variable loss. The current increase means the loss will also increase. But this is the constant loss, almost constant. It will not change with respect to the current. Now we will see what is the hysteresis loss and eddy current loss. So hysteresis loss, this is due to the reversal of magnetization of the armature core. Every portion of rotating core passes under N pole and S pole alternatively, thereby attaining N and S polarity respectively. The core undergoes one complete cycle of magnetic reversal after passing under one pair of pole. So in order to rotate, we are creating N pole and S pole alternatively. The winding connections are given in such a way that it will create N pole, next by S pole alternatively it will create. So this reversal of magnetization, due to the reversal of magnetization, the losses occur, that is called a hysteresis losses, that is given by this B power 1.6 max F into V. F is the frequency and that V is the velocity, right. So this is the formula for a hysteresis loss. Then we will go to the eddy current loss. When armature core rotates, it cuts the magnetic flux. The armature winding, actually armature winding should cut the magnetic flux, but armature windings are placed in the core. So the core also cut the magnetic flux. So due to that, EMF is induced in the body of the core. Normally what we need is the EMF should be induced in the armature winding, but armature winding is placed in the armature core. So in that core also cut the magnetic flux and EMF also induced in the core, which cause the current to circulate in the body of the core, which is called a eddy current, right. The EMF induced in the core of the core, due to that current circulate, that is called a eddy current. The loss due to the flow of this current is called a eddy current loss. It is K into B max square F square T square into V square, right. So this is the magnetic field intensity, magnetic flux density, frequency, thickness and velocity, right. So these two losses due to magnetic reversal as well as the EMF induced in the core. Now we will go to the third type, mechanical loss. So due to friction and windage, some losses will occur, that is called a mechanical loss. Friction means due to the friction. Windage is nothing but the force between the rotor and air, right. This is called a mechanical loss. So these loss also almost constant, it will not vary with the current, right. So that stray loss, we have one more term, the magnetic and mechanical losses together is called a stray loss, because these two are constant. Mechanical loss also constant, magnetic loss also constant. So by adding these two is given the new name stray loss. Now we will go to the next one. Further we have constant loss and variable loss. Again it is split into two major division. Constant loss. What is constant loss? The shunt and compound machine where the field winding is constant. The shunt field winding copper loss is also constant. If it is series field, mean when the current increases, the losses will increases. But in the shunt field, the current is almost same. The current will not increase, depends upon the load. So the shunt field copper loss also we can take it as a constant loss, right. So already we have constant losses available. This is called a stray loss, that is the sum of magnetic loss and mechanical loss. So the stray loss along with the shunt field copper loss is called a constant loss or standing loss, right. So the stray loss already we discussed, the sum of mechanical and magnetic loss. If you add the shunt field copper loss, because it is also almost constant, by adding these two we can take it as constant loss or standing loss. These losses are independent of the current. Then what about the variable loss? As the load increases, the armature current also increases, varies. The armature current depends on the load. So the armature copper loss vary with the load. Therefore, armature copper loss is called a variable loss, right. Either the armature winding or series field winding, when the load increases, armature current also increases, so that the losses also will increase. That is armature copper loss, right. So the total loss is nothing but constant loss plus variable loss. The constant loss is taken as WC. Variable loss is IA square into RA. Right? The loss due to the armature winding. Sum of these two is the total loss. WC plus IA square into RA. So in this video we discuss about the efficiency. In that efficiency, losses is the very important thing. The losses also we discussed majorly three types: copper loss, iron loss and mechanical loss. Right? Again further we classified into constant loss and variable loss. Right? Subscribe this channel for more videos. The link is available in the description box for other videos and the course material. Thank you. Welcome viewers. In this video we will see the power stages of a DC generator. Various power stages available in a DC generator. Subscribe this channel for more electrical related videos and notification. The soft copy of this material available in the drive link. The link is given in the description box. Now we will go to the topic. So the various stages of a DC generator is shown below. So it is classified into three stages: A, B and C. So the first stage is nothing but, so this DC generator is nothing but here, it converting the mechanical energy into electrical energy. That is mechanical rotation is converted into electrical output. So the DC generator we have the field winding and armature winding. We have two types, two things available. Armature winding is a rotating part. Field winding is a stationary part. So these windings are placed in a core, iron core, laminated iron core. So we have two main parts available. So the iron core is there over which windings are placed, both armature winding and field winding. So while the rotation, there are three type of losses will happen. One is loss happen in the copper coil itself, winding itself. Loss happen in the iron core. And the third one is the friction loss. So these three types are available. Now we will see that. So we have armature and field. This armature is connected to the either mechanical engine, diesel engine or petrol engine, or another DC motor. So the armature part of a DC generator is connected through the mechanical power input. So when the mechanical power input is given, that is the rotation, either diesel engine or petrol engine or DC motor rotates, the armature of the DC generator also rotates. The armature part start rotating. So when the armature of the DC generator rotates, so there is the iron loss will happen. The iron loss is nothing but loss happen in the core, laminated iron core. And also due to the rotation, the friction losses will happen. Right? So the armature part of DC generator is connected to either diesel engine or petrol engine or another DC motor. When it is rotating, the armature part also rotates. During the rotation, we have friction loss and also loss happen in the iron core. That is both field winding as well as the armature winding. So the remaining energy will be goes to the next stage, so that the electric power will be developed in the armature. So what is the principle? So already in the field winding, the field is available. Now in the armature is excitation is given. When a conductor cuts the magnetic flux, so this armature is rotating, so it will cut the magnetic flux produced by the field winding. So due to that, the EMF is induced in the coil. When a conductor cuts the magnetic flux, EMF is induced. So the EMF is induced in the armature, EG into IA, generated EMF into armature current. So it is available inside the generator. Right? So here armature rotates. Due to rotation, immediately we have friction loss and iron loss. Balance will goes to the next stage. In the next stage, due to rotation of this armature, that cut the field produced by the field winding. So whenever there is a change in field winding, the EMF will be induced in the armature. That is nothing but EG into IA, generated EMF into the armature current, EG into IA. But we have now the coil available. This EMF is induced in the coil, armature coil. So some losses will happen in the armature coil itself. So that's a copper loss. Some of the energy will be lost due to the copper. already some energy lost due to iron as well as friction. Balance is generated in the armature. Again, some of the losses will happen due to the copper. The remaining will goes to the output of the DC generator. That is nothing but V into I, terminal voltage into load voltage into load current, V into I, generated voltage and current. So this is the generated voltage and the current flowing through the armature. While going outside, some copper loss will happen. The remaining energy will be available at the output. That is nothing but V into I, the power output, voltage into current, right? So this is the three stages available. So the first, the mechanical energy is given through to the armature winding. So the armature winding rotates. Immediately the loss happen in the iron core, friction loss will happen. Remaining will goes to the next stage. So due to the change in flux in the field winding, the EMF is induced in the armature, that is Eg into Ia. Again, there will be some losses due to copper, due to the winding. So the remaining energy will be available at the output, right? So that we have A, B, C. Based on that, we'll go to the efficiency, various efficiency available in the DC generator. So the mechanical efficiency is given by, it is B by A, second stage to first stage. What is the second stage? Output by input. The efficiency refers output by input. The output is power developed in the armature. The input is mechanical power input. So the mechanical efficiency is available between first stage and second stage. So output is power developed in armature divided by mechanical power input. Then the second stage, electrical efficiency, C by B, third stage divided by second stage. Electrical power output divided by power developed in the armature. So that is power developed, C by B. So first mechanical power input, for that the output is power developed in armature. Power developed in armature, thus for that the next output is electrical power output. So this is can be given as V into I, the voltage and current available output of the output terminal of the generator. The power developed inside is Eg into Ia. So by combining these two, we can go with a overall efficiency or a commercial efficiency. That is C by A. The third stage divided by first stage. Third stage is electrical power output. First stage is mechanical power input. So that can be simplified as the commercial efficiency equal to, we can multiply with mechanical efficiency into electrical efficiency, Nm into Ne. So the mechanical efficiency is B by A, electrical efficiency is C by B, B got cancelled, so C by A. Third stage divided by the first stage. So we can go for three different efficiencies: mechanical efficiency, electrical efficiency, the last one is the overall or commercial efficiency. But in general, normally the efficiency refers power output divided by power input. What is the output we are getting divided by what is the input we are giving into 100 will give the percentage of efficiency, the general term. So the power output we can take as it is. Power input is nothing but the power, when the power is given, it will be converted into output power, but some losses will be there. So the input power is nothing but output power plus losses. By adding the output plus losses, we will get the input power. So we can replace P in as P out plus losses into 100. So both with the value of P out, we can able to find the overall efficiency in general. Power output divided by power output plus losses into 100 will give the general efficiency. So in this video, we discuss about the various stages of a DC generator. The soft copy of this material available in the drive. The link is given in the description box. Also subscribe the channel for more electrical videos. Thank you. Welcome viewers. In this video, we will see the condition for maximum efficiency in a DC generator. So subscribe the channel for more electrical videos and notifications. The soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. So we need to find the condition for maximum efficiency. So that efficiency is nothing but power output divided by power input. So first we will find what is the generator output, what is the generator input, then we will find the efficiency, then we will go for a condition for efficiency. So first we will find the what is the output of a DC generator. So the output of DC generator is V into IL, the line current or load current, V into generated EMF into IL. The EMF generated inside, so this V is the voltage available outside after the losses, V into IL. So we know that the armature current equal to load current plus shunt current. The sum of these two is the armature current. But the shunt current, we are assuming that it is very small, so that only we have load current. So we can take it as armature current equal to load current, that is equal to I, because the shunt current is very less. So we can replace this IL equal to I. So we have only one current, that is equal to armature current or the load current. So the generated output equal to V into I. Then what is the generated input? So when generated input is nothing but it's output plus losses. When the input is given to the generator, it will convert it into output, but some losses will happen. So the input is now changed into output plus losses. So by adding output plus losses, we can get the input. So what are the losses available? So now we have the output is already available here. Output is V into I. Now we can calculate losses. Variable loss plus constant loss. Variable loss means that is due to the copper. This friction and iron loss is the constant loss. That will not change, it depends upon the current. But variable loss, copper loss will change with respect to the current. So that it is called a variable loss. Now we will see what is variable loss and constant loss. So the variable loss equal to Ia square into Ra, the loss available in the armature winding. We already discussed that Ia equal to IL equal to I, right? There is only one current, that is equal to armature current and load current. So that we can replace Ia by I square Ra. So the variable loss equal to I square Ra. What is the constant loss? Constant loss is shunt copper loss and stray losses. So these are all constant, it will not change with respect to the current. So that is WC. We will take this as a WC. It is not variable, it is always constant. It is irrespective of the current. So that we can find the generated input equal to output plus losses. What is the output? V into I. The output is Vi. Then losses, two losses, variable loss and constant loss. Variable loss is I square Ra. Constant loss is WC, right? So that when the input is given, the generated, that will be converted into output and some losses will be there. So while adding output with losses, we can get the input. Now we got the expression for output as well as input. Output is Vi, input is Vi plus I square Ra plus WC. So from this we can able to find the efficiency. What is the efficiency of the DC generator? So the efficiency equal to output divided by input. So output is Vi, voltage and current available at the output of the output terminal. The input is Vi plus I square Ra plus WC. So output divided by input. We need to find the maximum efficiency, condition for maximum efficiency. When this efficiency will be maximum, for what condition? So this efficiency or loss is purely based on the current. When the current increases, the losses will increase. So the efficiency is purely depends upon the current, because the current is responsible for losses. This copper loss, armature copper loss. So when losses increases, automatically the efficiency will decrease. So we'll take this current as a important parameter to find the maximum efficiency. So on dividing and numerator and denominator by Vi, we are dividing the numerator and denominator by the term Vi in order to bring into 1, right? So this Vi is divided by Vi, the denominator also divided by Vi, so that the originality will not change. So this Vi by Vi is 1. So here Vi by Vi is 1. I square RA by VI. So one I got cancelled. So IA by V. Here is as it is WC divided by VI. Right? This term is splitted into 3. So that this I got cancelled here. Here one I got cancelled. So we got 1 divided by 1 plus IRA divided by V plus WC divided by VI. Now the efficiency term is simplified like this. So in order to get the maximum efficiency, what is the condition for maximum efficiency? For maximum efficiency, the efficiency to be maximum, the denominator should be minimum. If the denominator is minimum, that is the loss. If the loss is minimum, automatically we will get the maximum efficiency. So that we can apply the maxima minima theorem. What is that maxima minima theorem? We can differentiate the denominator term with respect to current, because the losses are based on the current. So differentiate the denominator with respect to current and equating 0 will get the condition for maximum efficiency. Right? So what is the term available in the denominator? 1 plus IRA divided by V plus WC divided by VI. So this term should be minimum, so that we are differentiating with respect to current and equate to 0. Why we are differentiating with respect to current? The current is responsible for the losses. When the current increases, losses will increase. Right? Now we'll go for the differentiation. So this differentiation of 1 is 0, constant. So IRA divided by V. We are differentiating with respect to I, so that this I become 1. So R by V. For example, dx. We differentiate with respect to dx, x equal to 1. Similarly, we are differentiating with respect to I. So this I become 1 R by V. RA by V. So here I available in the denominator. So what is the differentiation of 1 by x? Minus 1 by x square. Similarly, this 1 by I is minus 1 by I square. This WCV written as it is. Right? So the differentiation of 1 by I is minus 1 by I square. That is equal to 0. It is very similar to differentiation of 1 by x is minus 1 by x square. Similarly, here we have minus 1 by I square. Now we will go for the further simplification. So that RA by V minus WC divided by VI square equal to 0. Now bring this term from left hand side to right hand side, so that it become positive, negative become positive. RA by V equal to WC divided by VI square. Right? So this VV got cancelled. RA equal to WC divided by I square. Right? So bring this I in the left hand side. So I square RA equal to WC. What is I square RA? That is nothing but variable loss. What is WC? Constant loss. So if the variable loss is equal to constant loss, both are equal, then we will get the maximum efficiency. If the constant loss and variable loss are equal, we will get the maximum efficiency. Right? So it is given. Generator efficiency is maximum when I square RA equal to WC. That is, variable loss is equal to constant loss. So for that, what is the expression for current? I square RA into omega C. For that, we can find what is the current expression, so that we can maintain this current. The load current corresponding to the maximum efficiency is given as I square RA equal to WC. So bring the RA in the denominator. So I square equal to WC divided by RA. So this take square root on both the sides. So I equal to WC divided by RA. So we can find the load current for the maximum efficiency from this expression. I equal to WC divided square root of WC divided by RA. So in this video, we discuss about the condition for maximum efficiency. What is the condition? Correspondingly, what is the expression for the current? So subscribe this channel for more electrical videos and notification. The soft copy of this material available in the drive. The link is given in the description box. Thank you. Welcome viewers. In this video, we'll see the characteristics of self-excited DC generator. Subscribe the channel for more videos. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic, self-excited DC generator. So we know that there are two type of generator available, self-excited and separately excited DC generator. The separately excited DC generator, the characteristics available in the separate video. One more video available. Here we are dealing about the self-excited. So what is meant by self-excited? The excitation given itself, the generator itself, that's called a self-excited. So we know that there are two important parts available in the generator, that is armature and field. So this is the field coil, this is armature. Armature is the rotating part, field is the stationary part. The magnetic field is created in the field winding. So this armature is the rotating part. So here both are connected in parallel. This armature in parallel with that the field winding is connected. So that it is called a self-excited. There is no separate excitation required for this field winding. The energy available from the generator itself used to excite the field winding. It's called a residual magnetism. Thereafter the current generated from the generator itself used for excitation. That's why it is called a self-excited. In separately excited mean this field winding is connected separately, independent of armature. Right. So the field winding, stationary part, armature, rotating part, both are connected in parallel. So that is called a self-excitation. Due to residual magnetism at the initial, later on the energy, the current generated in the generator itself used for excitation purpose. So the first characteristic we are going to see the open circuit characteristics or no load characteristics or magnetizing characteristics. Open loop, this generator is not loaded, there is no load, only magnetization. During excitation, how the coil is magnetized. So the first characteristics is open loop or no load or magnetizing characteristics. So this is a generator terminal, load terminal, this is open circuited. There is no connection in the load terminal, open circuited. So across the armature the voltmeter is connected. So it will read the no load EMF. This field winding is connected through the ammeter, so it will read the field current. It is connected to the rheostat, variable rheostat. So the current flowing through this field winding can be varied by using this rheostat. And also it is connected through the switch S2. So we can open or close the current supplied to the field winding by using this switch S2. Right. So this ammeter will read the field current. This voltmeter will read the no load EMF. So we are going to draw the graph between this field current and no load EMF for various set of readings. IF, the E0 is noted down and the graph is drawn between this field current and no load EMF. Now we'll go to the another part, this motor. This generator is rotated by this motor circuit. Because we need to generator mean we need to rotate. We need to rotate the armature. So that is rotated by this motor. Both are identical machine, was coupled together. So this motor is given by this supply, DC supply, through the SPST switch, single pole, single thrown switch, through the 3-point starter. This is called a line, field and armature. This 3-point starter, the video available in separate video available. You can see that separate video available what is 3-point starter. So here also we have armature and field. This armature, this is a field. Field is connected through this 3-point starter, the point field connected through the resistor R1. So that by adjusting this resistor, we can control the current flowing through the field winding of a motor. So in 3-point starter, L is connected to the line, A is connected to the armature, F is connected to the field winding through the resistor. Right. Now this generator coupled with the motor, these two sets available. Now we'll go to the experiment. So initially the S2 is in the open condition, S2 is not connected. This totally all are open condition. First we need to run the motor, then only we can go to the generator. In order to run the motor, this SPST switch is closed and supply is given and SPST switch is closed, so that the supply is given to the motor. Now we can vary this resistor R1 in such a way that in order to bring the motor in the rated speed, by varying this R1, slowly by varying this R1, the the current flowing through the field winding keep on increases and it will start rotate at the rated speed. At the time now the field current is 0. There is no field current because it is in a open condition. Field current is 0. But due to residual magnetism in the field winding, there is some magnetic field is created. Some magnetic field is created due to the residual magnetism. Right? Now the supply is given, switch is closed, field current is varied so that the motor is rotated at the rated speed. So the generator also now rotating at the rated speed. But the switch is open, so there is no EMF generated, but due to residual magnetism, this field winding having some magnetic force. Now the switch S2 is closed, so that now the current will start flow in the field winding. Switch S2 is closed. The R2 is slowly adjusted. By varying the R2, we can set the field current. For the corresponding field current, we need to note the no load EMF. Again, the resistor value is varied, the field current is increased. For that increased value, again E0 is noted. Right? So for various set of readings IF, by varying this resistance value, the current flowing through the field winding keep on changes. So initially it is minimum value and keep on increases. For every field current, the no load EMF is noted down. Now we have set of readings for IF as well as E0. By using that, we can draw the open circuit characteristics or no load characteristics. Right? So now we'll explain again. The supply is closed, supply is given, switch is closed. So the supply is given to the motor. By adjusting this resistor R1, the current is flowing through the field winding. So the motor start rotate. The R1 is adjusted in order to bring the motor in the rated speed. So the motor is coupled with the generator, so the generator also rotates. But the switch S2 is open condition. Due to residual magnetism, some magnetic force available in the field winding. When S2 is closed, the current will start flowing through the field winding. So we can note down the field current value with respect to this E0, no load EMF. By varying this R2, we can vary the field current. For every field current, we can note down the no load EMF. Now we have set of readings E0 and IF. Using that, we can draw the graph. No load characteristics are open circuit characteristics. So this flux, when the field current increases, the flux also increases. So that the E0 also increases. All are proportional. Right? Field current increase means the flux will increase. The flux increase means the EMF also increases. Right? So it is under open circuited condition. The circuit is not closed. The load is not closed. Now we'll go to the graph, open circuit or no load characteristics. Now we have the set of readings available for this field current IF versus E0. So the graph is drawn between this field current and E0. By varying the resistor R2, we can set the value of field current. For every field current, the E0 value is noted down. So by using this value, we can draw the graph called a open circuit characteristics. So this is nothing but open circuit characteristics. See that when the field current increases, the E0 value also increases. At this point, it is saturated. So slowly increases, because when IF increases, flux will increase. When flux increases, the no load EMF also increases. So this is the open circuit characteristics, OCC. See this, it is even at the field current is 0, some value of no load EMF is available called RB. That is called a residual magnetism. Due to residual magnetism, even the field current is 0 at this point, we have some amount of no load EMF. This is due to residual magnetism. Now we have the points available. This is A1, the 0 is A1. At this minimum value, residual magnetism is B1, then C1, D1, this is E1. This point is P2. Right? Now we discuss about the open circuit characteristics with the residual magnetism, and the points are available. Now we can draw the RC line. What is RC line? It is nothing but tangent to the OCC curve. We need to draw the tangent. This is nothing but a tangent, right? So here this is given as a point A. This is nothing but a tangent. And one more line is RF line. RF line is drawn between this RF and VF, voltage across the field and current through the field winding. So it is almost this value is available. This is RF line. We have separate circuit is available how to take the reading this for this RF line, right? So where this RF line cut the OCC curve is the P2, where the tangent cut the OCC curve is P1, right? We have 2 points P1 and P2. Now where the tangent cut the OCC curve, this P1 is given, corresponding values are noted: no load EMF and the field current E01 and IF1, right? So we drawn the tangent RC, the tangent cut the OCC curve at point P1. At this point we are measuring the corresponding value of no load EMF and field current. So that is termed as IF1 and E01. So from this E01 and IF1, E01 divided by IF1 will give the critical resistance. Critical resistance R equal to V by I. V is E01, I is IF1. So we can measure from the graph, we can measure this two value. From that we can calculate the critical resistance. What is critical resistance? It is the maximum value of field current, field resistance above which machine failed to excite. The excitation will not happen. The maximum value of the resistance. If the resistance of the machine is more than that, mean the field coil will not excite. It should be less than. It is a maximum value. Thereafter, if the value increases, the machine fail to excite. So we can measure the critical resistance from these two values, E01 and IF1. Right. Now we'll go to this line. Now one line is drawn by covering this OCC curve and RF line, right? So this value is nothing but a no load EMF, maximum value. Thereafter it is constant E0, the point X. So one more line is drawn by covering this RF line, OCC curve and this RC line. This point A, point B, point C, right? So from this line what we can measure? This BC. The BC divided by AC will give the critical speed. So this value B up to from this point B to C. This is one value BC. From AC, BC divided by AC will give into rated speed will give the critical speed. We can measure one more value from this graph, that is called a critical speed. What is critical speed? It is the minimum speed of the generator below which machine failed to excite. It's the minimum speed. Thereafter, after that speed only the machine will excite. If the speed is less than that critical speed, mean machine will not excite. It's a minimum speed required to excitation. It's called a critical speed. That is measured by BC divided by AC. Right? Critical speed is the minimum speed of the machine below which machine is failed to excite. Right? So from this graph we can measure two parameters, critical resistance and critical speed, right? So from the set of, I will explain again, from the set of readings, field current and no load EMF, this OCC curve is drawn. You can see that clearly there is some voltage available even at the field current is 0, that is called residual magnetism, RV. These points are available, A1, B1, C1, D1 and E1. Now one tangent is drawn, that is called RC line. Where it cuts the OCC curve is point P1. The corresponding value E01 and IF1. From that we can measure critical resistance. And RF line is drawn. We will see what is RF line, how to draw the separate circuit available. Right. So at that point is again one more line is drawn, that is point A, B, C. BC divided by AC will give the critical speed. Right. So from this graph we can measure critical resistance and critical speed. Right. Now we'll see the description one by one. to draw RC line. It is a tangent drawn to the initial portion or linear portion of the OCC curve from the origin to meet the curve at the point P1. Right? The RC line is nothing but a tangent drawn to the OCC curve. Where it cuts is nothing but point P1. Then critical resistance. Now we discuss about the critical resistance. What is critical resistance? The slope of A1 A dash B1 will give the value of critical resistance RC. That is, let E01 be the corresponding to the point P1 and IF1 be the field current at point P1. Right? At A1 A dash P1 will give the critical resistance. For that corresponding values are E01 and IF1. So E01 divided by IF1 will give the critical resistance. What is critical resistance? Critical resistance is the maximum value of the field resistance above which machine failed to excite. It is a maximum value. If the resistor increase above this value, the machine will not excite. Right? Now we will see the RF line. What is RF line? So for RF line, we need to have one more separate circuit is available. It's a field winding. It is supplied by the DC supply through the switch S2, through this switch SPST. Across one voltmeter is connected, so that you will measure VF, field voltage. In series with that, one ammeter is available, so it will measure field current. It is connected through the rheostat. So we can vary the current flowing through the field winding by varying this resistor. Right? So we have the 230 volt, 220 volt DC supply, switch is available, resistor available to vary the field current, ammeter is used to measure the field current, voltmeter is used to measure the field voltage. Right? Now we'll see the procedure. Give the supply to the field winding. Supply is given. Connect voltmeter and ammeter in series with that we connected. By varying the R step by step, we can able to note down the value of IF and VF. Right? We need to vary this resistor. For every variation, we can note down the IF value and VF value. From this IF and VF set of value, we can draw the graph. That is called a RF line. This already we discussed in the graph, OCC graph. The RF line is extended to meet the OCC at point P2. It is extended to meet y-axis at point X. Right? And A dash X equal to E0. This is the rated no load value of EMF. That also we discussed in the graph. No load EMF obtained at this point where OCC curve RF line intersect each other. Right? So the RF line is nothing but where this EMF, no load EMF obtained at the point where OCC and RF line intersect each other. Right? Now we'll see what is the critical speed. What we discussed in the graph. Critical speed. Take any value of field current IF2 at point C on the x-axis and extend it up to and upwards. That we already discussed. So it cuts the RC line at 2 at point A and RF line at point B. Right? A is at the point A is available at the RC line and B is available at the RF line. So from that, BC by AC into rated speed will give the critical speed. Right? BC by AC will give the rated speed. So critical speed. What is critical speed? Critical speed is the speed corresponding to the critical resistance, or critical speed is the minimum speed of which generator below which the machine failed to excite. Right? If the speed is below that, it will not excite. It's a minimum speed required to excite. Right? Now we'll go to the other characteristics. Now we'll see the external characteristics. So after voltmeter reading reads the no load voltage, close the DPST switch and load the generator. For each load, note down the V and IL. So the previous characteristics is the no load characteristics. The generator is not loaded. Now the generator is loaded. For every load, we need to note down the terminal voltage and load current V and IL. Now the graph is drawn between the terminal voltage and the load current IL. But as the load increases, there is a drop in voltage due to armature resistance drop and armature reaction drop, right? So there is some drop available, that is first one is armature resistance drop IARA and armature reaction drop. Then we'll see the diagram. So the graph is drawn between this load current and terminal voltage IL and V. So this is the no load EMF, this no load current, no load characteristics, right? So due to armature reaction, the voltage is reduces. So this line, this is called actually this is called internal characteristics, right? Thereafter again armature resistance drop is there. So further the voltage is reduces. So this is called external characteristics. That is this one available internally in the generator, inside the armature. Only due to armature reaction is available, this value available inside the generator. Thereafter again we will go into the load N, we have some more drop, that is called armature resistance drop. So this is further the voltage is reduced. So this line refers the external characteristics, right? So first one is the no load characteristic, inside some armature reaction drop available, so the voltage reduces, that is called internal characteristics. Further the voltage reduces by armature resistance drop, that is called external characteristics, right? So this drop is drawn between E0 and IL. Now we'll see the internal characteristics. We already discussed, just we will see the graph. So it is obtained by adding IARA drop to the external characteristics, right? External characteristic, if you add IARA as an internal characteristics, I already discussed in the previous graph itself, right? So no load characteristics mean the entire voltage available. In that, if you subtract the armature reaction drop, then we'll get the internal characteristics. Further, if you reduce the armature resistance drop, we'll get the external characteristics. So in this video we discuss about the characteristics of self-excited DC generator, starting from no load characteristics, external characteristics and internal characteristics. In no load characteristics we can measure the two parameters from the graph, critical speed and critical resistance. Subscribe the channel for more videos. The link is available in the description box, the soft copy of this material. Thank you. Welcome viewers, in this video we will see the characteristics of a DC generator. Subscribe the channel for more electrical videos. Soft copy of this material available in the drive, the link is given in the description box. Now we will go to the topic, characteristics of a DC generator. The working behavior of DC generator under different conditions are studied and the graph or curve are exhibited between the various condition or quantities are called the characteristics curve. For different conditions, the different parameters are considered. Based on that, the graph or the curve is drawn. That is nothing but a characteristics of a DC generator. So there are three type of characteristics available. The first one is the magnetization or open circuit or no load characteristics without any load. So that is called a no load characteristics, or it is a open circuit. The load is not connected, so open circuit, or a magnetization characteristics. The second one is internal or total characteristics. The voltage or current available inside is the armature. Then external or load or performance curve. The current and voltage and the available in the output outside, the output terminal, load terminal. That's called a external or load or performance curve. So the magnetization or open or no load characteristics. Second one, internal or total characteristics. Third one, external or load or performance curve. Now we'll see what are the parameters available under this. In this magnetization characteristics, it is the graph drawn between no load EMF and field current. No load EMF and field current, that is called a magnetization characteristics or open circuit or no load characteristics without any load. So it shows the relation between the EMF generated in the armature at no load and the field current given at a given fixed speed. Without having the load, what is the EMF generated in the armature E0 for a given field current. So the relation between E naught and IF is given by the magnetization characteristics or no load or open circuit characteristics. Then internal characteristics. So internal characteristics is drawn between EMF generated versus armature current. EMF generated versus armature current. It gives the relationship between the EMF E actually induced in the armature after allowing the demagnetization effect of armature reaction and the armature current. Right. So it will give what is the relation between armature current and EMF generated inside the armature. The third one is the external characteristics. It gives the relation between the terminal voltage of V and load current. So it is going to the outside, output side, terminal voltage and load current IL. So it will give the relation between V and IL. So initially we are giving the field current, the excitation. So that is called a magnetization curve. Thereafter EMF is induced in the inside the armature. So that is the internal characteristics. So after some drop, after the losses, the voltage available at the output side, that is called a external characteristics. External characteristics, terminal voltage and load current IL. Now we will see the characteristics one by one. Now we will see the characteristics of a separately excited DC generator. So we know that there are two types available, separately excited and self-excited. So this one is separately excited, that is the field coil is excited separately, right. So the two major parts available in the DC generator, that is field and armature. So this is armature, this one field. The field is excited separately, that's why it is called a separately excited DC generator, right. So this one is the armature. So in this we have DC supply is available, across that the rheostat is connected in order to control the flow of current. So that is connected to one ammeter and it is connected to the field coil of the DC generator, right. So by adjusting this rheostat we can control the current flowing through the field winding. Then the EMF generated in the armature can be measured by this voltmeter. So we have one ammeter to measure the field current, voltmeter to measure the no load EMF. The current flowing through this field coil can be varied by using this rheostat, the variable resistor. So initially this rheostat is adjusted so that the current will flowing through this field winding. The corresponding the no load voltage will be read by the voltmeter. So we need to note down the ammeter reading and voltmeter reading, that is the value of the field current IF and no load voltage E naught. Then slowly this IF value is increased by adjusting this rheostat. For every reading we need to note down what is the value of IF and what is the value of E naught. So from the set of values we can draw the graph between this field current and no load EMF. So from this graph it is clearly given, it is clearly understand that when the field current increases, the no load voltage also keep on increases, right. It slowly increases, right. So we are taking the reading of IF and E naught for various values by adjusting this rheostat. From that value the graph is drawn. It is clear that when the field current increases, the no load EMF also increases. So here we have two things available, before saturation and after saturation. Now we will see how it will increases. What is the relation between this field current and no load EMF? So the Eg equal to pi n Z divided by 60 into P by A. It's a general formula, induced EMF in a generator. Pi n Z divided by 60 into P by A. Pi is nothing but flux, number of conductor, speed of the generator divided by 60, number of poles and number of the parallel path. So in this Eg is directly proportional to pi, which is directly proportional to IF. So that this pi and IF as well as Eg all are directly proportional. When the IF increases, the pi will increase, so that induced EMF also increases. So from this, when the IF increases, Eg also increases. So that's why we are getting the graph like this. When IF increases, the E naught also keep on increases, right. Now we will see the description one by one. the field is excited from a separate supply and the supply is varied by the rheostat, right? So that is called a separately excited DC generator. Initially the generator is made to run at this rated speed by adjusting the prime mover, right? By adjusting the prime mover, the generator is allowed to rotate at the rated speed. Now RF is varied and the ammeter and voltmeter readings are noted. By varying the RF slowly by using the rheostat, the ammeter and voltmeter readings are noted. The ammeter will give the field current, voltmeter will give the no load EMF. The RF is adjusted until E0 reaches its rated terminal voltage, right? For various set of reading, the RF is keep on adjusted until E0 reaches the rated value. We need to continue the same process. As IF increases, E0 also increases until the core saturated, and after saturation of the pole, the curve becomes the constant. Once it is saturated, the curve become constant. Until that is keep on increases, right? So this is the no load or saturation characteristics. That is the graph drawn between field current and no load EMF. Now we'll go to the internal and external characteristics. In internal and external characteristics, the field rheostat is adjusted until the no load EMF reaches the value at the rated terminal voltage, right? Until the EMF reaches this no load value, this rheostat is adjusted until the rated terminal voltage. So after that, the field current is kept constant at this value, right? Thereafter, we are not varying the field current. Now the generator is loaded because it is first characteristics is no load characteristics. Internal and external characteristics are loaded characteristics. Now the generator is loaded and the terminal voltage is obtained from the voltmeter. Now we are loading the generator. The terminal voltage starts dropping as the load increases, right? And the terminal voltage under the no load condition, it will give the constant value. Once it is loaded, the terminal voltages keep on decreasing when the load is increases. Now we'll see why it is decreasing. Now refer this graph, the graph drawn between IA and E0. So this is the no load EMF. It's called a no load EMF, right? We have two different drop available, armature reaction drop and armature resistance drop. So in this no load, while the generator is loaded, so it's a armature reaction will happen. Due to the armature reaction, the voltage is slightly reduces. So it is called a internal characteristic. E versus IA, right? EMF versus current IA is nothing but the internal characteristics. From that, again, the armature resistance drop will be there. In the armature coil, some amount of resistance available. So due to that resistance, the armature resistance drop will happen. That is IA into RA, right? So due to that, again the characteristics of this characteristics curve again decreases, right? This is called a external characteristic because this V and IA, V is available at the external terminal. So that it is called a external characteristics, right? V versus IA. So this dotted line refers the normal characteristics, no load characteristics. While loading, what will happen? Armature reaction happen. So the voltage is slightly reduces. That is called a internal characteristic, E versus IA. Thereafter again the voltage reduces due to the armature resistance drop. So that is called a external characteristics. Now we'll see what is mean by armature reaction drop and armature resistance drop. The distance between the curve 1 and 2 at every point loading condition give the armature reaction drop, right? So due to the armature reaction, the flux is reduced and the induced EMF also reduced, right? So due to that armature reaction, what will happen? The flux reduces, so that the induced EMF also reduces. As the load, then we'll go to armature resistance drop. As the load increases, the load current IL increases, hence IA also increases. So due to that, IA RA drop also increases, right? So V equal to E minus IA RA. So this drop is increasing, so that as increase in IA RA, the value of V decreases at the loaded condition, right? So from no load, due to armature reaction drop, some voltage reduces, that is called internal characteristics. Further, the voltage reduces due to armature resistance drop, that is called a external characteristics. So in this video we discuss about the what are the characteristics available of a DC generator, then characteristics of a separately excited DC generator, that is no load characteristics, and internal and external characteristics we discussed, right? Subscribe this channel for more videos. The material available in the drive, the link is given in the description box. Thank you. Welcome viewers, in this video we will see the characteristics of a DC generator, DC series generator. We know that in DC generator there are majorly two types available. One is self-excited generator, separately excited DC generator. Separately excited means the field is excited separately. Self-excited means field is excited in the generator itself. Again there are three types available: shunt generator, series generator and compound generator. How the armature and field, this is armature as a field, how the armature and field are connected, accordingly it is classified. If it is series generator mean this armature and field are connected in series, right? This armature is nothing but rotating part, the coils are available. This is a field, the stationary part, the magnetic field is created in the stationary part. So both are connected in series, that's why it is called a series generator. Now we will see the characteristics. So that there are three different characteristics available: no load characteristics, external characteristics and internal characteristics. But in series generator it is always started with the load, so there is no load characteristics available, only directly it is the external characteristics is available. Now we will see the diagram. So this is a generator available, the rotating part, this is nothing but a brush. So field coil is available, all are connected in series. In order to control the current flowing through the armature, the resistor is available. By adjusting that we can control the flow of current. This is the load terminal, right? This V is the load voltage. So inside the generator the current is generated, this is called armature current. So that is flowing through the series field winding, so ISC. That same current is flowing through the load also, that is IL. So IA equal to ISC equal to IL, because all are connected in series. Armature, field, load, all are connected in series. So the armature current is equal to series field current as well as load current. First we will see the external characteristics, that is V versus IL. This external. Internal means inside the generator, external means load side. The load side, terminal voltage versus load current, V versus IL, right? Now we will see the description. Only when the load increases, the load current IL also increases. While increasing the load current will increase. So IA equal to IL equal to ISC. So if ISC increases, all the current will increase. As the current through the series field winding ISC increases, the flux increases, right? Because all currents are equal. So when the load is increases, the load current will increase, so that ISC current also increases. If ISC current flowing through the series field increases, mean flux also increases. So the flux is directly proportional to the EMF. So the EMF also increases, the induced EMF also increases, right? So when the load increases, load current will increase, series field current will increase. Series field current increase mean flux will increase, so that EMF also increases. So there is a directly proportional. So when the load current increases, the V also increases, right? Is after saturated is slowly decrease, right? So it is both are linear, almost linear. When the load increases, the voltage also increases, EMF, induced EMF also increases, so that the current, the voltage available outside the voltage available at the load also increases. So we get the rising characteristics. Rising characteristics means when the load current increases, the voltage increases, rising characteristics. Decrease in voltage due to the armature reaction drop is negligible as compared to increase in EMF, right? Armature reaction drop is negligible, it is very slow, because it is rising characteristics. Now we'll go to the internal characteristics, the EMF induced inside the generator. So this is the internal characteristics. So external characteristics. So it is obtained by adding IA into RA plus RSC drop to the external characteristics, right? The resistance drop, the armature resistance drop, right? The EMF induced inside, armature resistance is drop, balance will be available outside, right? So this is the external characteristics what we discussed earlier. If we add the armature resistance drop, because here armature as well as field are connected in series, so we need to add both IA RA. If it is shunt generator, only IA RA will be available. Because of series, it is IA RA plus RSC, both are connected in series, right? So this is nothing but internal characteristics. Now we'll see in another direction. So this is the voltage induced inside the generator, right? Voltage induced inside the generator. Thereafter some drop is available inside the generator, armature resistance and field resistance drop. So due to that some voltage is reduced. This reduced voltage is available at the output side, external characteristics, right? Now we'll go to the compound generator. So the compound generator means the series field and shunt field both are available. Series field as well as shunt field both are available. If series field and shunt field are added together means it's called a cumulative compound generator. If both are oppose each other means differential compound generator, right? So it is divided into two parts. Either the both the field will be added, then or both the field will be oppose each other, right? So under that, so if the both the fields are oppose each other means this characteristics drawn between the load terminal voltage and load current is keep on decreasing. That is already we discussed due to armature reaction drop and armature resistance drop, as well as this is a differential compound. The series field and shunt field are opposing each other. So there is a drop in the voltage, right? When the load current increases, there is a drop in the voltage. So this last curve, this curve refers the differential compound generator. That why it is dropping? First one is due to differential. The fields are opposing each other. Apart from that, we have armature resistance drop as well as armature reaction drop is available. These three curve refers the cumulative compound generator. Cumulative compound generator means series field and shunt field are added together. Again, there are three types available. Over compound, we will see what is meant by over compound. So this is the no load EMF. Over compound means the voltage available above that, above the no load EMF. Under compound means it is available below the no load EMF. Flat compound means it is almost near to the no load EMF, right? So there are three types, either over compound or flat compound or under compound. Now we'll see what is meant by these three types. So cumulative generator means if series field add shunt field, this is called a cumulative compound generater. In that first type is the over compound. Rated voltage at generator is greater than the no load voltage, right? The no load voltage, the rated voltage is greater than the no load voltage. That's why it is called a over compound. Under compound means rated voltage is less than the no load voltage, right? Under compound. If it is flat component means both are equal. Rated voltage is equal to the rated no voltage, rated no load voltage, right? Based on that is classified into three. Then we'll see the differential compound. If series field oppose shunt field, it is called a differential compound generator. So in this video we discuss about the characteristics of series generator as well as compound generator, right? Internal characteristics as well as external characteristics. In case of compound generator we discuss differential compound and cumulative compound. Again there are three types: over compound, under compound and flat compound. Subscribe the channel for more videos. Soft copy of this material available in the drive. The link is given in the description box. Thank you. Welcome viewers. In this video we will see the solved problem based on the EMF equation of a DC generator part 1. Subscribe the channel for more videos. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the problem. A 4-pole wave wound DC generator has 50 slots and 24 conductors per slot. The flux per pole is 10 milliweber. Determine the EMF induced in the armature if it is rotating at a speed of 600 rpm. So based on the given data, we need to find the EMF induced in the armature. First we will see what are the data available. The number of poles is given as 4. It is given as wave wound DC generator. So number of parallel path is always equal to 2. For a wave wind, it is number of parallel path equal to 2. In case of lap winding, number of parallel path is equal to number of poles. But here given wave winding, so number of parallel path is always 2. Then number of slots is given 50. 50 slots are available. So conductor per slot is 24. So 24 conductors available in each and every slot. So that the total number of conductors equal nothing but Z is nothing but conductors per slot into number of slots. So the conductor per slot is given as 24. In each and every slot 24 conductors are available. So there are 50 slots are available. So 24 into 50, 1200. So the number of conductors equal to 1200. Right. So the number of conductors calculated from two data, conductors plus per slot into number of slots. From that we calculated there are 1200 conductors available in the generator. Then flux per pole is 10 milliweber. So milli means 10 to the power minus 3. So 10 into 10 to the power minus 3 Weber. And speed is given as 600 rpm. So these are all the data available. Now we'll go to the induced EMF. Only one parameter we need to find induced EMF. So the formula is pi n z divided by 60 into P by A. The pi is nothing but flux, n is speed, z is number of conductors divided by 60 into P is number of pole divided by a parallel path, number of parallel path. So all the data are available. The flux is 10 into 10 to the power minus 3. Number of conductors we calculated 1200. Then speed is given as 600 rpm divided by 60 into number of pole is 4. Number of parallel path is equal to 2 because of wave winding. So by simplifying this we got 240 voltage. The EMF induced in the generator is 240 voltage. Now we'll go to the second problem. An 8-pole DC generator has 500 armature conductors and useful flux of 0.5 Weber per pole. What will be the EMF generated if it is lap connected and runs at 1200 rpm? What must be the speed at which it has to be driven to produce the same EMF if it is wave connected? So originally it is a lap connected. For that we need to find the EMF induced for the given data. And one more question is, what is the speed for the same EMF induced? What is the speed if it is connected as a wave connected? Now we will see the given data. So first we will consider the lap connected. The original it is lap connected. So the number of poles equal to 8, P equal to 8. So number of parallel path, A equal to P, number of parallel path equal to number of poles, that is equal to 8 because of lap connector. In lap connector, number of parallel path equal to number of pole. Then number of conductor given as 500. The flux is 0.05 Weber per pole and speed is 1200 rpm. For this data we need to find what is the EMF induced for a lap connector. So the EMF induced, the formula is pi n z divided by 60 into P by A. Flux, number of conductors, speed divided by 60 into number of parallel path divided by number of pole divided by number of parallel path. Right? Flux is 0.05 and the number of conductor is 500. It is rotating at a speed of 1200 rpm divided by 60 into number of poles equal to 8, number of parallel path also 8, right? So by simplifying this, what we got? 500 voltage. The EMF induced for a lab connected for this given data is 500 voltage. Now with this 500 voltage and given data, now we need to go with a wave winding. If the same machine is connected from lab winding to wave winding, what is the EMF, what is the speed of the motor? What is speed of the generator? When it is wave connected, the important thing is number of parallel path equal to 2. Right? For a wave connected, always irrespective of the number of pole, the parallel path is always 2. The speed for the same EMF. Right? We know the formula for EMF. E equal to pi n z divided by 60 into P by A. Right? Now we bring this all other term in the left hand side except the speed, so that E into 60 into A divided by pi ZP equal to n. Right? The 60 and A is brought in the left hand side numerator. This pi Z and P is brought into the left hand side denominator. Right? So from this we can write it as n equal to E into 60 into A divided by pi Z into P. Right? So these data are already available. Only the parallel path is now considered as 2. This EMF induced we already calculated for the lab winding is 500. Right? So that you need to substitute all the value. EMF is 500 into 60 into number of parallel path equal to 2 divided by flux 0.05 into number of conductors 500 and the number of pole equal to 8. So by simplifying this, what we got? 300 RPM. So for the same machine, for the same EMF, when it is changed from lab winding to wave winding, we calculated the speed as 300 RPM. So in this video, we discuss about the EMF induced in the DC generator part 1. We discuss the two different problems. For this second problem, first we consider the lab winding, we calculated induced EMF. With that induced EMF, then we changed it into wave winding. For that we calculated the speed of the DC generator. Right? So subscribe this channel for the more videos. Soft copy of this material available in the drive. Link is given in the description box. Thank you. Welcome viewers. In this video, we will see the solved problem based on the EMF equation of DC generator, second part. Subscribe the channel for more videos. The soft copy of this material available in the drive. The link is given in the description box. Now we will go to the first problem. A 4-pole DC generator runs at 750 RPM and generated an EMF of 240 voltage. The armature is wave connected and has 792 conductors. If the total flux from each pole is 0.0145 Weber, then what is the leakage coefficient? We need to find what is the leakage coefficient for the given data. The EMF also given. Right? Now we will see what are the data available. So the number of pole equal to 4. Speed is given as 750 RPM. EMF induced 240 voltage. Number of conductors Z equal to 792. It is wave connected, so that number of parallel path equals always equal to 2. Then the flux is given 0.0145 Weber. Now we need to find what is the leakage coefficient. Right. The leakage coefficient is lambda is given as total flux per pole divided by useful flux per pole. Right? Total flux means the flux totally available. After the leakage, the useful flux after this flux flowing through the air, the remaining flux is called a useful flux. So the total flux is given in the problem. Total flux per pole is given in the problem as 0.0145 Weber. Now we need to find what is the useful flux. Useful flux means normal flux, what we are referring in the equation. Right? Now we need to find useful flux so that we can calculate the leakage coefficient. How will you find the leakage total flux? The EMF is given. The EMF value is given in the problem itself. So we can refer this pi n z divided by 60 into P by A. By referring this formula, we can find the useful flux. Because total flux is given, this is nothing but useful flux. All other data are available, only pi is not available, so that we can calculate the pi value. Now bring the all other term in this left hand side. This 60 into A is brought into left hand side numerator, 60 into A. This NZP is brought into left hand side denominator, so that E into 60 into A divided by NZP equal to pi. So that can be written as pi equal to E into 60 into A divided by NZ into P. The EMF is given as 240 into 60, number of parallel path equal to 2 because of wave connected. The number of conductors Z is 750. The speed is 750. Number of conductor Z is 792 into number of pole is 4. Right? Now all the data are substituted. By simplifying this, what we got, 0.01212 Weber. See this, which is less than the total flux. This is the total flux. In this much of flux only utilized as a useful flux. Now we got the useful flux value, so that we can calculate the leakage coefficient. So the leakage coefficient is lambda is nothing but total flux per pole divided by useful flux per pole. Total flux is given 0.0145 divided by useful flux we calculated 0.01212, so that it is 1.19. The leakage coefficient is 1.19. Now we will go to the second problem. The armature of a 6-pole DC generator have wave winding containing 650 conductors. Calculate the generated EMF when the flux per pole is 0.055 Weber and the speed is 300 RPM. Calculate the speed at which the armature must be driven to generate an EMF of 550 voltage if the flux per pole is reduced to 0.05 Weber. Right? So first we need to find the generated EMF for the given data. The speed, everything is given. Then we need to find the speed if it is the EMF is 550 voltage and the flux is reduced 0.05 Weber. For this different data, we need to find the speed of the generator. Now we will see what are the data available. So the number of pole is given as 6. It is wave connected, so that number of parallel path is always 2. The number of conductor is 650. Flux is given, this original value 0.055 Weber. Then speed is 300 RPM. So this is the normal data. For the second part, we need to find the speed. For that, EMF is 550 and flux is reduced to 0.05 Weber. Now we will go to the first part, A. All data are available. We need to find the EMF. Pi n Z divided by 60 into P by A. The flux is 0.055 into the number of conductors 650 into speed 300 divided by 60 into number of pole is 6 divided by number of parallel path equal to 2. Right? By simplifying this, what we got, 536.25 voltage. Right? For a given data, the induced EMF is 536.25 voltage. Now we need to find the speed of the speed for the second case. If the flux is reduced to 0.05 and induced EMF is 550 voltage. Then how will you find the speed? We can use the same formula. E equal to pi n Z divided by 60 into P by A. From that we can find the n. 60 and A is brought into left hand side numerator. N, this pi Z, P is brought into left hand side denominator, so that n is this. So by rewriting this, n equal to, this pi is not there, n equal to E into 60 into A divided by pi Z pi n into P. So the speed is given as n equal to E into 60 into A divided by pi Z into P. So generated EMF is 500 voltage is given, 60 into number of parallel path equal to 2 because of wave connected, divided by the flux, the reduced flux is given 0.05 into number of conductors 650 into number of poles 6. So by simplifying this, what we got, 333.46 rpm for the 500 voltage EMF and reduced flux 0.05. The speed is 333.46 rpm. Now we'll go to the third problem. A dynamo has rated armature current of 250 ampere. What is the current per path of a armature if the armature winding is lap or wave connected? The machine has 12 poles. So in this problem, the armature current is given, number of pole is given. We need to find current per path. If it is lap connected, what is the current per path? If it is wave connected, what is the current per path? So we'll go to the given data. So the current is given, armature current is 250 ampere, number of pole equal to 12 voltage. Now we'll consider the lap connected. So the number of parallel path in case of lap connected, A equal to number of poles. So that is equal to 12. The P is given as 12. So in case of lap connected, the number of parallel path is equal to number of poles, which is 12. So current per parallel path equal to IA divided by A. IA is given 250. Now the parallel path equal to 12. So 250 divided by 12 is 20.833 ampere. So current per path equal to 20.833 amperes for a lap connected. Suppose if it is wave connected. If it is wave connected, the number of parallel path always 2. It is irrespective of the pole. A is always 2. In previous case, the A equal to 12 equal to number of poles. Now it is 2. So the current per parallel path equal to IA divided by A. So 250 divided by 2, that is equal to 125 ampere. So in case of wave connected, the current per path is 125 ampere, which is more than the lap connected. So for wave connected, it is used for high current rating machines. For high current rating machine, we are using wave connected. For high voltage rating, we can use the lap connected. So in this, we discuss the 3 different problems based on the EMF generated. Subscribe the channel for more videos. Soft copy of this material available in the drive. The link is given in the description box. Thank you. Welcome viewers. In this video, we will see the solved problem based on the types of the DC generator, part 1. Subscribe the channel for more videos. Soft copy of this material available in the drive. Link is given in the description box. Now we'll go to the first problem. A 250 voltage 100 kilowatt separately excited DC generator has an induced EMF of 255 volt at full load. If the brush drop is 2 voltage per brush, calculate the armature resistance of the generator. The question is, we need to find the armature resistance of the generator. Now we'll see the data, what are the given data available and what is the diagram. So this is separately excited DC generator. Separately excited means we have 2 main parts available in the DC generator, the armature, rotating part, and field coil is a stationary part. These field coils are excited separately by the DC source. So that is called a separately excited DC generator. Self-excited means both are connected together, armature and field. This is separately excited. So this is the rotating part, armature. This is the stationary part, field winding, which is excited separately by the DC source. Now we'll see that this is RF. This is a field coil. The current flowing through this IF, field current. In this rotating part, armature, we have RA, armature resistance. The current flowing from the armature is IA. While going to the load, it is IL. So IA is equal to IL, both are equal. Here the generated EMF is given as 255 voltage. The voltage available outside is 250 voltage. So after the drop 255, after some drop, remaining 255 voltage is available at the load end. So we'll see the data. So V equal to 250 voltage. Terminal voltage is 255, 250 voltage, but the generated voltage is 255 voltage. The power output is 10 kilowatt, that is 10 into 10 to the power 3 watts. The brush drop is 2 voltage per brush. So there will be minimum of 2 brushes are available. So this is a brush 1 and brush 2. For we need a minimum 2 brushes. So the total brush drop is nothing but 2 voltage into 2 brush, that is equal to 4 voltage. Right? We need to find the resistance RA. Our aim is to find the resistance RA. Now we'll go to the description. Output power is given. So P equal to V into IL, terminal voltage into load current. So P equal to V into IA, because IA equal to IL. We clearly given in the diagram, the current coming from the armature is equal to load current. Both are equal. So from this equation we can find IA equal to P divided by V, power divided by terminal voltage. The power is given as 10 into 10 to the power 3, 10 kilowatt, divided by the terminal voltage is 250. So by dividing this we got 40 ampere. The armature current is equal to 40 ampere. Our aim is to find the resistance. So we'll go to this equation. So generator, for separately excited DC generator, the generated EMF is equal to the voltage available at the load end, armature resistance drop plus brush drop. Right? So the generated voltage is converted into, mostly is converted into terminal voltage, but some of the voltage is dropped across the armature resistance, some voltage is dropped across the brush drop. So this is a basic equation for separately excited DC generator. So from this we can write it as Eg minus V minus Ia Ra minus brush drop equal to 0. Right? We'll bring this Ia Ra in the right hand side. So Eg minus V divided minus brush drop equal to Ia Ra. So that we can write Ra equal to Eg minus V minus brush drop divided by Ia. Right? So from this basic equation, after simplification step by step, finally we got the armature resistance is Eg minus V minus brush drop divided by Ia. So all these values are available. The generated voltage is 255. The terminal voltage is 250, brush drop we calculated 4, and the armature current is 40 ampere. That's now we calculated. So by simplifying this value, we got Ra equal to 0.025 ohm. Armature resistance is 0.025 ohm. Now we calculated the armature resistance. Now we'll go to the second problem. A DC series generator. So this problem based on the series generator has an armature resistance 0.5 ohm and series field resistance RAC is series field resistance 0.03 ohm. It drives a load of 50 ampere. It has 6 turns per coil and a total of 540 coil on the armature and is driven at 1500 RPM. Calculate the terminal voltage at the load. So the question is, we need to find the terminal voltage. Assume 4-pole lap type winding. The flux per pole is 2 milliweber and total brush drop is 2 voltage. Right? So this is the data. We will see the data one by one. Armature resistance is 0.5 ohm. Armature resistance is 0.5 ohm. Series field resistance RSC is 0.03 ohm. The load current is 50 ampere. The speed is 1500 RPM. Number of pole equal to 4. Lap winding, so that the number of parallel path equal to number of pole, that is equal to 4. In case of lap winding, the number of parallel path is equal to number of poles. The pole is given 4, it is, so that number of parallel path also 4. The brush drop is 2 voltage. So it is given total brush drop. So the brush drop of both the brush is 2 voltage. The flux is given 2 milliweber. So that 2 into 10 to the power minus 3 Weber. 2 milliweber. So that it is milli means 10 to the power minus 3. The number of turns per coil is 6. Total number of coil is 540. right? Our aim is to find the terminal voltage at the load. Now we'll see the diagram. So in this series connected generator mean armature and field both are connected in series. So this is series generator. The important part is the armature, rotating part, which is the field, stationary part. Both are connected in series. So that is called a series generator. Right? This is the load terminal. The EG is the voltage induced in the series generator. RA is the armature resistance. So this voltage generated induced in the series generator is EG. Now we need to see the current. The current flowing from the armature is IA. The same current is flowing through the series field ISC. The same current is flowing through the load also. So the current from the armature, series field and load all are equal, all are same because of series circuit. IA equal to ISC equal to IL, all are equal, right? Now we'll see we will go to the topic. Number of conductors equal to 2 into number of turns, Z equal to 2 into T. So that is a formula. Now number of turns equal to number of turns per coil into number of coils. Right? So these two data are available. Number of turns per coil is available, that is 6. The number of coils available is 540. So multiplying this, the number of turns is 3240. Right? From that we can find the number of conductors. Number of conductors is 2 into T. So because two sides available, so number of turns into 2 will give the number of conductor. So 2 into 3240. So the number of conductors equal to 6480. So the number of conductor Z is 6480. This number of conductors not given, but number of turns per coil, number of coil is given. From that we can calculate the number of turns. From the number of turns we can calculate the number of conductors. Now we'll go to the next parameter. So for a series generator, the generated EMF is equal to terminal voltage plus armature resistance drop as well as series field drop, RA and RSC. RA refers the armature resistance. RSC is the series field resistance. So both are connected in series so that we can add IA into RA plus RSC plus brush drop. Right? So the generated voltage is converted into terminal voltage and drop across the armature and drop across the series field, then drop across the brush. So from this we can write V equal to EG minus IA RA plus RSC minus brush drop. Right? So this EG is, this V is kept here, these three terms are brought in the other side, so that we got like this. So we can calculate the terminal voltage by using this formula. So IA, RA, RSC, all the values are available, but EG is not available. So we need to find the EG, generated EMF. For that another formula available. Pi n Z divided by 60 into P by A. So these data are available. From that we can calculate EG. By using EG and other value we can calculate terminal voltage. Right? So pi is nothing but 2 milliweber. So 2 into 10 to the power minus 3. Number of conductor, just now we calculated 6480 into the number of speed of the generator is 1500 divided by 60 into number of pole is V 4 and number of parallel path also 4. So by simplifying this we got 324 voltage. The generated voltage is 324. By using this we can go for a terminal voltage. So for series generator, IA equal to IL equal to 50 ampere. Both are equal. Armature current is equal to load current, that is equal to 50 ampere. So V equal to EG minus IA RA plus RSC minus brush drop. Just now we framed this equation. Now we can substitute the value. So the EG we calculated 324 minus the armature current is 50 ampere. So both are equal. Load current is equal to armature current. The armature resistor is 0.5 and series field resistor is 0.03 minus total brush drop is given 2 voltage. So by simplifying that we got 295.5 voltage. The terminal voltage is 295.5 voltage. So in this video we discussed two problems. One is based on the separately excited DC generator. Second one based on the series generator. Subscribe the channel for more videos. The soft copy of this material available in the drive. The link is given in the description box. Thank you. Welcome viewers, in this video we will see the solved problem based on the types of DC generator. Subscribe the channel for more videos. Soft copy of this material available in the drive. The link is given in the description box. Now we will go to the first problem. A 4-pole DC shunt generator. So this problem is based on the shunt generator with a shunt field resistance of 100 ohm and armature resistance of 1 ohm has 378 wave connected conductors in the armature. The flux per pole is 0.02 Weber. If a load resistance of 10 ohm is connected across the armature terminal and the generator is driven at 1000 rpm, calculate the power absorbed by the load. Right? So this is DC shunt generator. Finally, we need to find the power absorbed by the load. Now we will see the data, what are the data available and also the diagram. So the number of poles is given as 4 pole. The shunt field resistance is 100 ohm and armature resistance 1 ohm. Number of conductors 378. Because of wave connected, the number of parallel path equal to 2. The flux is 0.02 Weber. The load resistance is 10 ohm and the generator is rotating at a speed of 1000 rpm. So because of shunt generator, we have two important components. One is rotating part armature and another one field coil, field winding, the stationary part. These two are connected in parallel. That's why it is called a shunt generator. This is the load terminal with a voltage of V. V is the load voltage. So this RAC is the resistance of the shunt field winding. RA is the armature resistance. Now we will see the generated EMF. The EMF generated in the generator is EG. And IA is the current flowing from the armature. So at this point the current is diverted. This current is flowing through the load is called IL. Current is flowing through the shunt field is ISC. So IA equal to IL plus ISH, sum of these two. Right. So shunt field as well as field winding and armature are connected in parallel. That's why it is called a shunt. It's called shunt generator. The important thing we need to remember, the IA equal to IL plus ISH. Based on the diagram, it is clearly we can able to observe that IA equal to ISH plus IL. Right. Now we'll go to the parameter. First we will find the armature current. So we know that from the diagram IA equal to IL plus ISH. So the IL can be calculated as V divided by RL, load voltage divided by load current. Similarly, ISH can be calculated as V divided by RSH because the field is connected, all are connected in parallel. So the same voltage we can use for shunt field also, divided by RSH. So V is common. So 1 divided by RL plus 1 divided by RSH. Now we can substitute the value. The load resistance is 10 ohm, shunt field resistance is 100 ohm. Right. So by simplifying, we got IA equal to 0.11 ampere. It's not a voltage, 0.11 ampere. So the armature current is 0.11 ampere. Now we'll go to the generated EMF. Generated EMF EG, we know the formula pi NZ divided by 60 into P by A. So the flux is given 0.02 and number of conductor is 378. The speed is 1000 rpm divided by 60 into number of pole is 4 divided by number of parallel path is 2 because of wave connector. So by simplifying this, we got EG, generated EMF, equal to 252 voltage. Right. So armature current we calculated. Now the induced EMF also calculated. Our final aim is to calculate the power absorbed by the load. Then we will go to the terminal voltage. V equal to EG minus IA RA. Otherwise, EG equal to V plus IA RA. Generated voltage is converted into terminal voltage and sum of the voltage is dropped across the armature. It's a basic formula. From that we can find V equal to EG minus IA RA. So the EG we calculated 255 minus IA, the armature current just now we calculated 0.11 voltage into 1. So that voltage only, because the V value is not available. So that is 0.11 V only we got from the previous calculation. That's not a ampere, 0.11 V only. So 255 minus 0.11 V, right? So we bring this term in the left hand side. So V plus 0.11 V equal to 255. So that 1.1 V equal to 255. So that V equal to 255 divided by 1.1, that is 227 voltage. The voltage across the terminal is 227 voltage. Now the voltage is calculated. In order to go for the power, we need voltage and current. Now we will calculate the load current. Load current IL equal to V divided by RL. V is calculated 227 divided by the load resistance is 10, so that 22.7 ampere. Right. Now we calculated the load voltage as well as load current. From that we can easily calculate the power absorbed by the load. Power absorbed by the load is V into IL. Right. So 227 into 22.7, that is 5153 watts. Power absorbed by the load is 5153 watts. Right. So IA equal to 0.11 V only. V value is not available. Right. Now we calculated the power absorbed by the load. Now we will go to the second problem. A long shunt DC generator delivers a load current of 200 ampere at 500 voltage. The resistance of armature, series and shunt field are 0.03 ohm, 0.015 ohm and 150 ohm. Calculate the EMF induced in the armature. Allow a brush contact drop of 1 voltage per brush. So this problem is based on the long shunt DC generator. Long shunt, we will see what is meant by long shunt. Also we will see what are the given data available. So in the generator, the important two parts are armature, rotating part, and field, stationary part. Right. So in this long shunt mean, it is a coming under compound generator, that is both series field as well as shunt field. This series field and shunt field are available. It's a compound generator. There are basically three type available: shunt generator, series generator and compound generator. Compound generator mean both series field and shunt field will be available. Right. So immediately with the armature, series field is connected. With this combination, the shunt field is connected. So that is called a long shunt. Right. Armature is immediately connected to series field. Thereafter only it will go to shunt field. So that is called a long shunt. Similarly, short shunt is available. Short shunt mean immediately the shunt field is connected. Thereafter only series field. Here shunt field short shunt mean the shunt will be connected like this. So here it is a long shunt. So this is a terminal voltage available at the load end. RSH is the resistance of the shunt field. RSC is the resistance of the series field. RA is the resistance of the armature. EG is the generated EMF. Now we will see the current, that is very important. The current flowing from the armature is IA. That is same current is flowing through series field also. But at this point it is splitted. So IA equal to ISC, both are equal. Thereafter it is splitted. IL through the load terminal, ISH through the shunt field terminal. So that IA equal to ISC, that is equal to ISH plus IL. Right. From the diagram, it is very important to see the current direction and the current how it is divided. So the current divided at this point with ISH and IL. So the given data, the load current is given 200 ampere, the load voltage is 500 voltage, RA armature resistance 0.03 ohm, series field resistance 0.015 ohm, shunt field resistance 150 ohm, brush drop is 1 voltage per brush. So totally there are 2 brushes available. So 2 into 1, 2 voltage. Now we'll go to the current calculation. So for a long shunt generator, from diagram it is clearly given IA equal to IL plus ISH. The armature current is divided into load current and shunt field current. So the IL value already available. So ISH can be calculated V divided by RSH, because shunt field is connected, across the load only. So that the load voltage can be used for shunt field also, divided by RSH. Now all the data is available. Load current is 200 plus voltage is 500 divided by shunt field resistance 150. So by simplifying this, we got 203.33 ampere. The armature current is 203.33 ampere. Now we'll go to the induced EMF. Our final aim is to find the induced EMF. Eg equal to V plus Ia into Ra plus RSH plus brush drop. Right. So the induced EMF is converted into terminal voltage, drop across the armature and shunt field, then brush drop. Right. So here the series field is connected in series, so that it is not taken into account. So only shunt field is taken into account. So Eg equal to, we can substitute all the value, 500 plus 203.33, that is Ia we calculated, plus Ra 0.03 plus 0.015 plus brush drop is 2 voltage. So that is equal to, by simplifying this, we got 511.15 voltage. The generated EMF is 511.15 voltage. So in this video we discussed the two different problems. One problem is based on the shunt generator, second problem based on the long shunt generator. Subscribe this channel for more videos. The link is available in the description box. The drive for soft copy of this material. Thank you. Welcome viewers. In this video we will see the solved problem based on the types of DC generator, part 3. Subscribe the channel for more videos. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the first problem. A short shunt DC generator delivers a load current of 200 ampere at 500 voltage. So this problem based on the short shunt. The resistance of armature, series and shunt field are 0.03 ohm, 0.015 ohm and 150 ohm respectively. Calculate the EMF induced in the armature. The question is, we need to find the EMF induced in the armature. Allow a brush contact drop of 1 voltage per brush. The brush drop is 1 voltage per brush. Now we'll see the given data as well as the diagram. Short shunt DC generator. The load current is given as 200 ampere. The load current equal to 200 ampere. And the terminal voltage is 500 voltage. RA is 0.03 ohm, RSC 0.15 ohm, 0.015 ohm, RSH shunt field 150 ohm. Brush drop equal to 1 voltage per brush. So the total brush drop equal to 2 voltage, because there are 2 brushes are available. Now we'll see the diagram, what is meant by short shunt. So the short shunt or long shunt is coming under the compound generator. Compound generator mean both series field as well as shunt field are available. So this is a series field, this is a shunt field, both are available, so that it is coming under compound generator. In that, what is short shunt? This is the rotating part, armature. These two are stationary part, shunt field and series field. The main part of the DC generator, what we have, the rotating part armature, and stationary part the field winding, series field and shunt field. How we are connecting the field winding with the armature, accordingly it is classified. Now it is coming under short shunt, that is this shunt winding is connected immediately. Thereafter the series winding is connected. That's why it is called a short shunt. In long shunt mean immediately the series field will be connected. The combination of series field and shunt field across that, the armature across shunt field will be connected. Right. So in the short shunt, immediately with the armature the field winding, shunt field winding is connected. Thereafter series field winding is connected. So that it is coming under short shunt DC generator. Now we'll see the parameters one by one. So this is the load terminal, load voltage V. So this is the armature. Inside the armature the EMF is induced, that is Eg. EMF induced inside the generator is Eg. The resistance of the armature is Ra. The resistance of the shunt field winding RSH. The resistance of series field winding RSC. right? Now we'll see the current direction, that is very important. The current coming out of this armature is IA. IA is the current generator, EG is current voltage generator, in that we are getting the armature current. So at this point the current is splitted, ISH and ISC, shunt field current and series field current. So IA equal to ISC plus ISH, shunt field current plus series field current. So thereafter this series field current is going to the load terminal, this IL. So this ISC and IL are both are equal, same current is flowing through the series field as well as the load, right? So IA equal to ISH plus ISC, this ISC is equal to IL, series field current and load current are equal. So based on that we can go for the calculation. So for a short shunt DC generator, ISC equal to IL. This IL value already given is 200 ampere. So ISC also 200 ampere. So both are equal. Then IA equal to IL plus ISH. Just now we discussed in the diagram, right? So this IL is nothing but ISC. So IA equal to ISC plus ISH. ISC can be replaced by IL. Then how will you find this IL is already available? How will you find this ISH? This you can find the ISH by using this formula, VSH divided by RSH, right? Voltage across the shunt field divided by RSH, right? What is VSH? This is, here the shunt field is only connected across the armature, not a load, right? So that VSH equal to V plus ISC into RSC, the voltage across the shunt field. So the voltage across the shunt field equal to the total voltage plus this series field voltage, then only we can get the shunt field voltage. So VSH equal to V plus ISC into RSC, right? The V is available, terminal voltage is 500, ISC is just now we calculated is 200 ampere, into RSC is 0.015. So by simplifying this we got 503 voltage. So the voltage across the shunt field is 503 voltage. Now we can find the IA. IA equal to IL plus ISH. So IL is 200 ampere. This ISH is VSH by RSH. VSH now we calculated 503. RSH is 150 ohm. So by simplifying this we got IA equal to 203.353 ampere. So now we calculated the armature current also, 203.353 ampere. So by using the data we can go for a generated EMF. Our final aim is to find the generated EMF. So EG equal to V plus IA RA plus ISC RSC plus brush drop. The voltage generated inside the armature is dropped across the load terminal, then armature resistance, drop across the armature resistance, then series field resistance, series field drop, then brush drop, right? So this EG is converted like this, voltage across the load terminal, armature resistance drop, series field resistance drop and brush drop, right? All these values are available. The terminal voltage is 500, then IA is now just now we calculated 203.353 into RA is 0.03 plus ISC is 200, RSC is 0.015 plus brush drop is 2 voltage. So by simplifying this, by adding this we got 511.10 voltage. So the generated voltage is 511.10 voltage, right? Now we'll go to the second problem. A 20 kilowatt 200 voltage DC shunt generator has an armature and field resistance of 0.05 ohm and 150 ohm respectively. So this problem is based on the shunt generator, right? The power is given, voltage is given, field resistance and armature resistance is given. Determine the total power developed in the armature. Total power developed in the armature, right? Now we'll see the data one by one. The power given as 20 kilowatt, that is equal to 20 into 10 to the power 3 watts. The voltage is 200 voltage. Armature resistance 0.05 ohm. Shunt field resistance 150 ohm. We need to find power developed in the armature, not outside, inside the armature, PA. So PA, what is the PA? Eg into Ia, voltage induced in the armature into armature current. V into I, V is nothing but induced EMF, and Ia, right. Then how will you find this Eg? Eg equal to V plus Ia Ra. Then how will you find Ia? Ia equal to IL plus ISH because of shunt current, shunt generator. The Ia is splitted into load current as well as shunt field current, right. So by finding Ia, we can find the Eg. From Eg, we can find the power developed in the armature. So we will find this value one by one. First we will find the load current IL. IL equal to P divided by V. The output power and load voltage is given 20 kilowatt, 20 into 10 to the power 3 divided by 200. These two data load terminal. What we need to find is the power developed in the armature inside. These two data is available outside the load terminal voltages are available. So from that the load current is 100 ampere. We calculated load current equal to 100 ampere. Then ISC equal to V divided by RSC. Because shunt field, it is connected across the armature. The same voltage can be used for shunt field also. All are connected in parallel. So V divided by RSH. V is 200, RSH is 150. So that is equal to 1.33 ampere. Now we calculated the load current as well as shunt field current. So that we can calculate the Ia. Ia equal to IL plus ISH. So in the shunt generator, the armature current is splitted into load current and shunt field current. So 100 plus 1.33, so this 101.33 ampere. The armature current is 101.33 ampere. So from that we can find the EMF generated inside the armature, Eg equal to V plus Ia Ra. So V value is given 200 plus Ia is nothing but 101.33 into Ra is 0.05 ohm. So by simplifying, we got 205.0665 voltage. The EMF induced inside the armature is 205.0665 voltage. So from this we can find the power developed in the armature. PA equal to Eg into Ia. So Eg now calculated 205.0665 into the IL value also available, Ia value also available 101.33. So by multiplying this we got 20,779.388 watts. So power developed in the armature is 20,779 into 3.388 watts. See this, the power developed is more than the power available outside. This 20 kilowatt is available outside the load terminal. So the power developed inside is nearly 20,779. So after the drop, armature reaction drop and armature resistance drop, remaining power 20 kilowatt is available outside. So in this video we discuss about the short shunt, one problem based on short shunt DC generator and one problem based on shunt generator. Subscribe the channel for more videos. Soft copy of this material available in the drive. The link is given in the description box. Thank you. Welcome viewers. In this video we will see the solved problem based on the types of DC generator. This part 4. Subscribe the channel for more videos. The soft copy of this material available in the drive. Link is given in the description box. Now we'll go to the first problem. The resistance of the field circuit of a shunt excited DC generator is 200 ohm. So this problem based on the shunt generator, shunt DC generator. The output of the generator is 100 kilowatt and the terminal voltage is 500 voltage. So the output power and output voltage is given. The generated EMF is 525 voltage. This is our EMF generator inside the armature. So based on the data we need to calculate armature resistance, the value of generated EMF when the output of 60 kilowatt and the terminal voltage is 520 voltage. Right. The first question armature resistance. The second question we need to find the generated EMF for a 60 kilowatt. Already it is given as the power is given 100 kilowatt. Now it is changed to 60 kilowatt and the terminal voltage will be 520. For that we need to find what is the generated EMF. Now we will see the given data. So the RSH shunt field resistance is given 200 ohm. The power output power is 100 kilowatt, that is 100 into 10 to the power 3 watts. So kilowatt means 10 to the power 3. The terminal voltage is 500 voltage, generated EMF equal to 525 voltage. Now the first part we will go for the armature resistance. We will find the armature resistance. So we know that EG, shunt resistance, EG equal to V plus IA RA. It's a basic formula for shunt generator, right? Now we'll find the load current IL. IL equal to P divided by V, power divided by voltage. Both are available. Output power and terminal voltage is given 100 kilowatt, that is 100 into 10 to the power divided by 500. Voltage is 500. So that is equal to 200 ampere. So the load current equal to 200 ampere. Then shunt current, shunt field current ISH equal to V divided by RSH. Because the shunt field is connected across the load, so the load voltage can be used for finding the shunt current. All are connected in parallel. Armature, field, load all are connected in parallel. So the same voltage can be used for finding the ISH. So V equal to 500 divided by RSH is given 200 ohm. So that is equal to 2.5 ampere. The shunt field current equal to 2.5 ampere. Now we'll find the IA, armature current. IA equal to IL plus ISH. In case of shunt generator, the current generated from the armature is IA, that is splitted into IL and ISH. Current flowing through the load as well as current flowing through the shunt field, that is divided. So sum of these two is the IA. So 200 plus 2.5 will give 202.5 ampere. So the current flowing from the armature is 205.5 ampere. Now we need to find the RA. So from this formula, EG equal to V plus IA RA. From that, RA can be written as EG minus V divided by IA. It is simplified, rearranged. So that the EG value is, we know the EG value, it is 525 voltage. The terminal voltage is 500. This IA is 202.5. Just now we calculated IA. So by simplifying this, what got? 0.1234 ohm. The armature resistance is 0.1234 ohm. Now we'll go to the second part. The second part we need to find the generated EMF when the power is 60 kilowatt and the terminal voltage is 520 voltage. Right? For these two data we need to find what is the generated EMF. Right? So again we'll find what is the load current. Now the power and voltage is changed. So IL equal to P divided by V, 60 kilowatt, 60 into 10 to the power 3 divided by 520. So 115.3846 ampere. Right? So the shunt field current ISH equal to V divided by RSH. So the now V is 520 divided by 200 is 2.6 ampere. Right? For this given power and voltage, we calculated the load current and shunt field current. So the armature current IA is nothing but IL plus ISH. Because of shunt generator, the sum of these two is the IA. So these two we calculated 115.3846 plus 2.6. So the sum of these two is 117.9846 ampere. Right? Now again we are using the basic formula EG equal to V plus IA RA. Right? So here VG we need to find. V is given 520 voltage. IA just now we calculated 117.9846 into RA is 0.1234. That is we calculated in the earlier, the previous case. Same value we are using. Right? So by simplifying this we got 534.55 voltage. So which is greater than the load terminal voltage. Right? So from this the armature drop will be there. Balance will be available as a low terminal voltage. 534.55 voltage. Right? Now we calculated the generated EMF. We will go to the second problem. A 4-pole DC shunt generator with a wave wound armature having 390 conductors has to supply a load of 500 lamp, each of 100 watts at 250 voltage. Right? This is a shunt generator. 4 poles available, 390 conductors are available. The voltage is 250. The load is 500 lamps available with each of 100 watts. allowing 100 voltage for the voltage drop in the connecting leads. There is a 100 voltage, 10 voltage drop in the connecting lead between the generator and load. Brush drop of 2 voltage. There is a brush drop is 2 voltage is available. Calculate the speed at which the generator should be driven. We need to find the speed of the generator. The flux per pole is 20 milliweber. Then armature resistance is 0.05 ohm. Sun field resistance is 65 ohm. So these are all the data given. We will see the data one by one. The number of pole equal to 4. The number of pole given in this generator is 4. This wave winding is given. So that number of parallel path is equal to 2. For wave winding, the number of parallel path is always 2. Then the number of conductor is 390. Voltage is 250 voltage. The flux is 20 milliweber. That is 20 into 10 to the power minus 3 weber. Milli means 10 to the power minus 3. Then armature resistance 0.05 ohm. Sun field resistance 65 ohm. The total brush drop equal to 2 voltage. The given is the total brush drop. There are 2 brushes available. So totally there is a 2 voltage drop including 2 brushes. The drop in the lead is 10 voltage. Right? One more drop is drop in the lead. Then we need to find the power. How will you find the power? There are 500 lamp available, each 100 watts. So 500 into 100 will give the total power, 5000 watts. There are 500 lamp, each of 100 watts. So 500 into 100 will give the 5000 watts. So the load in the output power equal to 500 into 100 equal to 50,000 watts. That is 50 kilowatt. Not 5,000, it is 50,000. So from that we can find the load current P divided by V. 50,000 divided by 250 will give 200 ampere. The load current is 200 ampere. Now we will find the ISH. ISH equal to V plus voltage drop across lead divided by RSH. This V is available 250. The drop across the lead is 10 and RSH is given 65. So simplifying this we got 4 ampere. So the load current is 200 ampere. The sun field current is 4 ampere. So from that we can find the armature current IA. IA equal to IL plus ISH. In case of sun generator, this IA is splitted into IL and ISH. Right? So 200 plus 4 equal to 204 ampere. The armature current is 204 ampere. Now from that we can find the generated EMF. Finally we need to find the speed of the generator. Generated EMF equal to E equal to V plus IaRa plus brush drop plus lead drop. Right? The generated voltage is converted into terminal voltage, armature resistance, brush drop and lead drop. So 250 plus the Ia we calculated 204 into Ra is 0.05. The brush drop is 2 voltage. The lead drop is given as 10 voltage. So by adding this we got 272.2 voltage. The generated EMF is 272 voltage. Now we need to find the speed of the generator. For a generated EMF, one more formula is available in relating the speed. Pi NZ divided by 60 into P by A. The flux, number of conductors, speed divided by 60 into number of pole divided by number of parallel path. So by rearranging this we can write N equal to, you have to multiply this 60 into A in the numerator. This pi ZP is brought into denominator. So that N equal to E into 60 into A divided by P pi Z. Right? All these values are known. So E equal to 272.2. So just now we calculated. Into 60 into A, number of parallel path equal to 2 because of wave winding. Divided by number of pole is 4. The pi is given as 20 milliweber. 20 into 10 to the power minus 3. Number of conductor is 390. So by simplifying we got 1046.92 RPM. The speed of the generator is around 1046.92 RPM. So in this problem we discuss about the DC sun generator, problem based on the DC sun generator. Subscribe the channel for more videos. The soft copy of this material available in the drive. The link is given in the description box. Thank you. Welcome viewers. In this video, we'll see the solved problem based on the losses and efficiency of the DC generator part 1. Subscribe the channel for more video. The soft copy of this material available in the link. The link is given in the description box. Now we'll go to the problem. The armature and field resistance of 110 voltage sun generator running at 800 rpm are 0.12 ohm and 55 ohm respectively. So this is coming under sun generator. The speed is given, voltage is given, armature and field resistance are available. It supplies a 220 lamps of each rated 60 watts 110 voltage. The friction and vintage core losses of the machine is equal to 410 watts. Calculate armature copper loss on full load and sun field copper loss. Second one, mechanical, electrical and overall efficiencies. Now we'll see the data. What are the given data available? The voltage is given 110 voltage. The speed is 800 rpm. Armature resistance 0.12 ohm. Sun field resistance 55 ohm. 220 lamps are available with each 60 watts. So the power output equal to 220 into 60. 13,200 watts, right? There are 220 lamp available, each 60 watts. So multiplying this, we'll get the power output 13,200 watts. Friction and vintage loss plus core loss, that is called as a stray loss, is equal to 410 watts, right? Friction, vintage plus core loss is given, that is called a stray loss, that is equal to 410 watts. First we will find the armature copper loss. We will go to the armature copper loss. So for sun generator, IA equal to IL plus ISH. Armature current equal to load current plus sun field current. This is divided. Both are divided. So the sum of these two is the armature current. So the ISC can be calculated as V divided by RSH, because sun field is connected across the load and connected across the armature. So the same voltage is available across the armature as well as sun field. So 110 divided by 55, that is equal to 2 amperes. Sun field current is 2 amperes. Then the power output P equal to V into IL. So from that we can calculate the IL, because power value is available. Power we calculated 13,200. The V also available. So from that we can find the load current. So IL equal to P divided by V. So 13,200 divided by 110 voltage, that is equal to 120 ampere. So now we calculated the load current also. From that we can calculate the armature current. IA equal to IL plus ISH. So that is equal to 120 plus 2, that is 122 ampere. The armature current is 122 amperes. So with this armature value we can calculate the copper losses one by one. Armature copper loss equal to Ia square into Ra. The formula for armature copper loss is Ia square into Ra. So that is 122 square into 0.12. The armature current just now we calculated. So that is equal to 1786 watts armature copper loss. Then sun field copper loss, that is equal to ISH square into RSH. That is, this ISH is nothing but 2 ampere. So 2 square into 55, that is equal to 220 watts. So this is the sun field copper loss. So the total copper loss equal to 1786 plus 220, that is equal to 2006 watts. The total copper loss is 2006 watts. Now we can calculate the total loss. Total loss equal to total copper loss plus stray loss. The stray loss is given in the problem itself, 410. The total copper loss now we calculated 2006. So that the total loss will be 2416 watts. Right? 2416 watts is the total loss. So with this data we can go for the efficiency. that now we are having the data total loss, so that we can able to find the efficiency one by one. So the mechanical power input is nothing but power input plus losses. This mechanical input. So power input is 13,200 plus loss is 2,460. So totally the mechanical power input is 15,616 watts, 15,616 watts, right? The power input, electrical power input plus losses will give the mechanical input. By adding this loss and power input, we can get the mechanical power output, mechanical power input. So the power developed in the armature is nothing but this mechanical input minus stray loss. Once the mechanical input is given, some stray losses will be there. If we subtract the stray loss from the mechanical input, we can get the power developed in the armature. So 15,616 minus stray loss will give the 15,206 watts. So this is the power developed in the armature. So this is the power given, mechanical power given input. So from that, if you subtract the stray loss, we will get the power developed in the armature, right? Now we have the data mechanical power input, the total power input and power developed in the armature. So with this value, we can calculate the efficiencies one by one. So the mechanical efficiency is nothing but power developed in armature divided by mechanical power input, right? So mechanical power input is given at the time, the stray loss will be there. The remaining is nothing but developed in the armature. So that power developed in armature divided by mechanical power input will give the mechanical efficiency. These two data is available. 15,206 divided by 15,616 into 100. So that is 97.37%, right? The mechanical efficiency is 97.37%. Now we'll go to the electrical efficiency. So the electrical power output divided by power developed in the armature. Power developed in the armature, after that some copper loss will be there, remaining will be available as the electrical power output. So power developed in the armature is now calculated 15,206, right? But power output is 13,200. How the value is reduced? That is due to the copper loss, right? So 13,200 divided by 15,206 into 100, it will give 86.8%. So the electrical efficiency is 86.8%. Now we can calculate the overall or commercial efficiency, that is electrical power output divided by mechanical input. So this is the primary input, mechanical input. The primary output is electrical power output. In between what we have, power developed in armature. So that is due to the stray loss, thereafter copper loss. So different losses are available. So finally we are getting the electrical output. So the mechanical power input is 15,616 watts. Electrical power output is 13,200. So 13,200 divided by 15,606 into 100, it will give the 84.52%. So the overall efficiency is 84.52%. So in this problem, we discuss about the sun generator. For that, we calculated the copper loss, right? Armature copper loss followed by efficiency, mechanical efficiency, electrical efficiency and overall efficiency. Subscribe the channel for more videos. The soft copy of this material available in the drive. Link is given in the description box. Thank you for listening. Welcome viewers. In this video, we'll see the solved problem based on the losses and efficiency of the DC generator, the part 2. Subscribe the channel for more videos. The soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the problem. A sun generator has a full load current of 196 ampere at 220 voltage. The stray losses are 720 watts and shunt field copper resistance is 55 ohm. The stray loss means it is nothing but mechanical, windage and friction loss. If it has a full load efficiency of 88%, find the value of armature resistance RA. Also find the load current corresponding to maximum efficiency. So the efficiency is given, from that we need to find RA and also the load current corresponding to the maximum efficiency. Now we'll see the given data. So the load current is given 196 ampere. The voltage is given 220 voltage. Efficiency equal to 88%. The stray loss, that is mechanical and vintage loss, is 720 watts. The sun field resistance is 55 ohm. Right? Now we'll find the value one by one. First we will find the armature current. ISH equal to V divided by RSH, because armature current equal to IL plus ISH. In case of sun generator, the armature current is split into load current and sun field current. So that IA equal to IL plus ISH. The IL is given 196 ampere. ISH we can calculate from this V divided by RSH. The V is 220 divided by 55, it is 4 ampere. Right? So the ISH, the sun field current, is 4 ampere. The load current is 196 ampere. So that armature current IA equal to IL plus ISH. 196 plus 4 equal to 200 ampere. Now we calculated the armature current. So that we can calculate the other parameters, losses, one by one. Now we will find the copper loss followed by the armature resistance. So the power output is nothing but V into IL, because terminal voltage and load current is given, so that the power output, final output, can be calculated. V into IL, 220 into 196, 43,120 watts. So this is the final output, is calculated from terminal voltage and the load current. So what is the efficiency? Is power output divided by power input. So the power output is available and also efficiency also given, so that we can calculate the power input. What is the input power? So right, we need to interchange this. So power input equal to power output divided by efficiency. Right, by rearranging that we can calculate power input. The power output is we calculated 43,120 divided by efficiency given 88%, that is 0.88. So the power input, by simplifying that, with the power input is 49,000 watts. Right. So the power input to the DC generator is 49,000 watts. See this, the power input, the power output is lesser, because due to the mechanical friction and vintage loss, the sun field copper loss, armature copper loss, after all the losses are available. So by subtracting the losses from the input, we are getting this much of output. Now we'll go to the losses. Now we'll find the loss. So the loss is nothing but input minus output. The input, if you subtract the output from the input, you will get the total loss. Right, 49,000 is the total input power given. So this 49,000. So the power output is 43,120. Right. So by subtracting, we are getting 5,880. 5,880 watts is the total loss. Right, 5,880 watts. Right. So the losses we calculated, total loss is calculated, but the stray loss is already given, so that we can find the sun field copper loss. So this one, sun field copper loss is nothing but ISH square into RSH. So the ISH we already calculated 4 ampere into 55. So 880 watts. So the sun field copper loss equal to 880 watts. Right. So we know that constant loss equal to stray loss plus sun field copper loss. Why it is called constant loss? This loss will not vary with the current, armature current. Irrespective of the armature current, these two losses are always constant. This stray loss, that is already given, 720 watts. The sun field copper loss we calculated 880. These two are called a constant loss. It will not vary with the armature current. That is, it will not vary with the load. It is always constant. So the sum of these two is 1600 watts. Right. Now we calculated the constant loss. Right. What is the total loss? Total loss is nothing but armature copper loss and constant loss. Right. The total loss is nothing but the constant loss plus armature copper loss. But we know this total loss and constant loss, so that we can calculate copper loss. Right. From total loss, if you subtract the constant loss, we'll get the armature copper loss, right? So the total loss is 5880 minus the constant loss is 1600 watts. So by subtracting this, we got 4280 watts. So this is the copper loss, right? So first we calculated the power input. From the efficiency, we calculated the power output. From power input and output, we calculated the total loss. Then we calculated the shunt field copper loss. Then we calculated the constant loss, that is the sum of stray loss and shunt field copper loss, right? Then the total loss is nothing but constant loss plus armature copper loss. From that, we have calculated the armature copper loss, right? But armature copper loss, one more formula available, Ia square into Ra, so that we can calculate the armature resistance. That is one of the question we need to find what is the armature resistance, right? So the armature copper loss, one more formula, Ia square into Ra, so that Ra equal to armature copper loss divided by Ia square, right? So the armature copper loss is available 4280 divided by armature current is 200 square. So that Ra equal to 0.107 ohm. The armature resistance is 0.107 ohm, right? That is calculated from the one more formula, Ia square into Ra, right? Now we calculated the armature resistance. The one more question, we need to find the current corresponding to the maximum efficiency, right? So for a maximum efficiency, one condition is available, I square Ra into equal to Wc. What is this Wc? Wc is nothing but constant loss. This is nothing but variable loss. So the condition for maximum efficiency is variable loss equal to constant loss. This constant loss we know already is available, right? So from this equation, we can find I equal to Wc divided by Ra, square root of Wc divided by Ra, right? So the Wc already available, constant loss is 1600. Ra we calculated 0.107, right? So here Ra equal to I square equal to Wc by Ra, so that I equal to square root of Wc by Ra. So these two values are substituted. By simplifying, we got 122.28 ampere. So the current corresponding to the maximum efficiency is nothing but 122.28 ampere. So in this problem, we calculated the power input, power output, total loss, shunt field copper loss, then constant loss, then armature copper loss. From that, we calculated armature resistance and current for the maximum efficiency. Subscribe the channel for more videos. The soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we'll see the solved problem based on the losses and efficiency of the DC generator, part 3. Subscribe the channel for more videos. Soft copy of this material available in the drive. Link is given in the description box. Now we'll go to the problem. The following data pertains to a shorts and compound generator. So this problem is based on the shorts and compound generator. The armature resistance is 0.04 ohm. Series field resistance is 0.025 ohm. Shunt field resistance is 45 ohm. So the compound generator means we have both series field as well as shunt field. Then contact drop per brush is 1 voltage. The magnetic loss is 2.5 kilowatt. Mechanical loss is 1 kilowatt, right? The mechanical loss and magnetic loss are given. Find the efficiency of the generator when it is deliver 400 amp at a 440 voltage, right? We need to find the efficiency of the generator when it is deliver 400 ampere at a voltage of 440 voltage, right? I will see the analyze the data, what are the given data available. So the armature resistance is given 0.04 ohm, series field resistance 0.25 ohm, shunt field resistance 45 ohm, contact drop per brush, there are 1 voltage, but there are 2 brushes available, so the total brush drop equal to 1 into 2 voltage. The magnetic loss is 2.5 kilowatt, that is 2.5 into 10 to the power 3 watts. Then mechanical loss is 1 kilowatt, that is equal to 1 into 10 to the power 3 watts. Kilo mean we need to multiply with 10 to the power 3. The load current is 400 ampere. The voltage, terminal voltage is 440 voltage. Now we need to find the efficiency. Our final aim is to find the efficiency. First we will find the power output. What is the output power of this generator? So the output power can be calculated terminal voltage and load current. These two data are available, terminal voltage and load current. 440 into 400 ampere. So that it is 1,76,000 watts. Right, 1,76,000 watts is the power output calculated from terminal voltage and load current. For a short shunt generator, compound generator, ISH is nothing but VSH divided by RSH. So this VSH is nothing but V plus ISC into RSC divided by RSH, because short shunt means the shunt field is connected immediately, thereafter series field will be connected. So the terminal voltage plus series field voltage is nothing but shunt field voltage, right? So V plus ISC RSC divided by RSH. Then ISC equal to IL. The same current ISC is flowing through the load, both are equal. So that is equal to 400 ampere. IL is already given. So ISC also it is equals is 400 ampere. So from that we can calculate ISC. V plus ISC RSC divided by RSH. V is 440 voltage plus ISC is 400 ampere. RSC is 0.025 divided by RSH is 45. So by simplifying that we got ISC equal to 10 ampere. Now from that we can find the armature current. IA equal to IL plus ISH. Right? For a short shunt generator, the current is splitted into shunt field as well as load current. That is series field and load current are equal. So IL plus ISH will give the IA. So IL is already given 400 ampere, ISH we calculated 10 ampere. So 400 plus 10 will get 410 ampere. Now we got the value of armature current. From this we can calculate the losses one by one. So armature copper loss equal to IA square into RA. IA is already we calculated 410 ampere. So 410 square into RA is 0.04, that is equal to 6,724 watts. So the armature copper loss is 6,724 watts. Then shunt field copper loss, ISH square into RSH. Right? So the ISH already calculated 10 ampere. So 10 square into 45, that is equal to 4,500 watts. The copper loss in the shunt field copper loss 4,500 watts. Then series field copper loss, ISC square into RSC. ISC is equal to IL, both are same. So it is 400 square into 0.025, that is equal to 4,000 watts. Right? So we calculated the armature copper loss, shunt field copper loss, series field copper loss. Now the brush loss is VB into IA. The total brush drop is 2 voltage into IA. IA is 410 ampere. So 820 watts. So the 820 watts is dropped in the brush loss. Right? Now we calculate the 4 different losses. Right? Now we will calculate the total loss. The total loss is nothing but armature copper loss, shunt field copper loss, series field copper loss, magnetic loss, mechanical loss and brush loss. Right? So by adding all this we can get the total loss. All these values are available. Armature copper loss we calculated 6,724. Shunt field copper loss also we calculated 4,500. Series field copper loss we calculated 4,000 watts. Right? Magnetic loss, that is the brush loss, is 820. Then magnetic loss is given 2.5 into 10 to the power 3. Then mechanical loss also given 1 into 10 to the power 3. Right? So by adding all we can get this, we can get the total loss 19,544 watts. Right? The total loss in the generator is 19,544 watts. Now we already calculated the power input. Output power we already calculated from terminal voltage and load current. Now we got the losses. right? So from that we can find the power input. Power input is nothing but output power plus losses. When the power is given, some of the power is lost, the remaining power is given as a output power. So by adding the output power and loss, we will get the total power input given to the generator, right? So these two data are available. So 1,76,000 is the power output plus 19,544 is the total loss we calculated. So by adding this, 1,95,544 watts is the power input given to the DC generator, right? So this is the power input and this is the power output. So in between we have losses. In this power input, after the loss, this is the power output. Now we got the value of output power as well as input power, so that we can calculate the efficiency. So efficiency is nothing but output power divided by input power into 100. Output power is 1,76,000 divided by input power is 1,95,544 into 100, right? This value just now we calculated. So by simplifying this, what we got? 90%. The efficiency of this short shunt generator is 90%, right? So in this problem, first we calculated the power output. Then we calculated the armature current value. By using the armature current and shunt field current values are calculated. From that we calculated armature copper loss, shunt field copper loss, series field copper loss. From that we can calculate the total losses, that is nothing but armature copper loss, shunt field copper loss, series field copper loss, stray loss, that is the mechanical loss, magnetic loss, brush loss, right? Once you calculated the loss, simply we can calculate the input. Input is nothing but output plus losses, right? So with the value of power input and power output, we calculated the efficiency, that is 90%. Subscribe the channel for more videos. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we will see the solved problem based on the losses and efficiency of the DC generator, the part 4. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we will go to the problem. Find the efficiency at full load and half load for a 1200 kilowatt 600 voltage shunt generator using the following data. Armature resistance RA is 0.005 ohm, shunt field resistance RSH 60 ohm, brush drop equal to 1 voltage per brush, mechanical and iron loss at the rated load is 20 kilowatt. So these are all the data available. We need to find the efficiency at full load as well as half load. Now we'll analyze the given data. The output power is given 1200 kilowatt. Kilowatt means 1200 into 10 to the power 3 watt. The kilo means we need to multiply with 10 to the power 3. And armature resistance 0.005 ohm. Shunt field resistance RSH 60 ohm. The terminal voltage is 600 voltage. Brush drop equal to 1 voltage per brush, so that the total brush drop equal to 2 voltage. There are 2 brushes available, so 2 into 1, 2 voltage. Mechanical and iron loss. So it is known as a stray loss. Mechanical and iron loss together is also called as a stray loss, that is 20 kilowatt. It means 20 into 10 to the power 3 watts. So these are all the data available. From that we need to find the efficiency. First we will find the output power. Output power P equal to V into IL. This output power is given and the voltage, terminal voltage also given. So from that we can find the load current IL. IL equal to P divided by V. The P is given 1200 kilowatt. So 1200 into 10 to the power 3 divided by terminal voltage is 600. So that 2000 ampere. So the load current is 2000 ampere, that is calculated from given output power and terminal voltage. Then shunt field current ISH, that is equal to, because of shunt generator ISH can be written as V divided by RSH. because the sun field is connected across the armature, across the load. So the same voltage is applied across the sun field. So ISH equal to V divided by RSH. The V is 600 voltage divided by RSH is 60, that is equal to 10 ampere. For the sun generator, the armature current is equal to load current plus sun field current. The sun field current, this IL plus ISH, because the armature and load and sun field all are connected in parallel. So in this armature, the current coming from the armature is diverted into load current as well as sun field current. So sum of these two is the armature current. So these two values already we calculated, 2000 ampere and 10 ampere. So 2000 plus 10, 2010, 2010 ampere. Armature current is 10 ampere. So from this armature current we can calculate the copper losses. Copper losses one by one. So the armature copper loss equal to Ia square into Ra. This Ia is calculated 2010. So 2010 square into Ra is 0.005. So that is equal to 20,200 watts. Then sun field copper loss, ISH square into RSH. The ISH is 10 ampere. So 10 square into 60, that is equal to 6000 watts. So the sun field copper loss is 6000 watts. Then brush loss equal to VB into Ia. VB is the voltage drop at the brush, that is 2 voltage. So 1 voltage per brush, per 2 brushes mean 2 voltage. The Ia value is 2010 ampere. So that is equal to 4020 watts. Right. Then this is mechanical plus iron loss. Stray loss is already given in the problem, that is 20 kilowatts. So 20 into 10 to the power 3 watts. Right. So now we calculated armature copper loss, sun field copper loss, brush loss and stray loss, that is mechanical and iron loss. Now we will go to the total loss. So total loss equal to armature copper loss plus sun field copper loss, brush loss plus iron and mechanical and iron loss. We need to add all the values, right? These values are we already calculated. So by adding all these we got 50,220 watts, right? The total loss in the generator is 50,220 watts, right? Now we calculated the total losses. So we note that input equal to output plus losses. So the losses we calculated, output also already given. So by adding the output and loss, we can able to find the input to the generator. So right. So the output is 1200 kilowatt, 1200 into 10 to the power 3 plus losses is 50,220. That is equal to 1,25,220 watts. Right. So this 12 lakhs 50,220 watts. So it's not, it is 12 lakhs 50,220 watts, right? So when the input is given, that is converted into output and some losses will be there. So that by adding output and losses we are able to find the input. Now we have the input as well as output is available. From that we can easily find the efficiency. These are all for the full load value. So the output is 12,200 kilowatt divided by 12 lakhs 50,220 into 100, that is equal to 90.9%. So for this full load value the efficiency is 90.9%. Now we'll go to the half load. So half load, first we need to find the half load power. Half load output. What is the half load output? That is nothing but total output divided by 2, because half load only we are applying. So divided by 2. So that is 600 into 10 to the power 3 watts. That is 600 kilowatt. Right. So the power output at the half load is nothing but total power divided by 2. So correspondingly the total load current of the half power. Load current is IL equal to P divided by V, because the power is reduced, automatically the load current also will reduce, right? So IL equal to P divided by V. So 600 into 10 to the power 3 divided by the voltage is 600, that is nothing but 1000 ampere. The load voltage is 1000 ampere. Earlier it is 2000 ampere, now reduced to 1000 ampere. Then armature current Ia equal to IL plus ISH. This ISH is constant, it is 10 ampere, right? So the IL is now 1000 ampere. So 1010 ampere, right? Earlier it is 2010 ampere, 2020 ampere. Now it is reduced to the 2010 ampere, now reduced to 1010 ampere, this armature current. So due to half load, the power is reduced, load current also reduces, and armature current also reduces. So with this armature current, we can find the copper loss. We can repeat the process, same process again. Armature copper loss, Ia square into Ra. So 1010 square into 0.005, that is 5100 watts. Sun field copper loss, ISH square into RSH. So that is equal to 10 square into 60, that is 6000 watts. So this is independent of the load. So the same 6000 watts will be calculated for full load also. Then the brush loss, that is VB into Ia. So this is variable. Ia value is now reduced. So 2 into 1010, this is 2020 watts. Then mechanical and iron loss is already given, 20 kilowatt. So this is almost a constant. It will not vary with the load. So 20,000 watts. Now we can add all this so that we can calculate the total loss. Armature copper loss, sun field copper loss, brush loss, and mechanical and iron loss. By adding, we got 33,120 watts. Right? Now the total loss is calculated. The output power already is available. So from the output power and loss, by adding the output power and loss, we can able to find the input, because input is converted into output and some losses. So by adding output and losses, we will be able to get the input. Right? So 600 into 10 to the power 3 plus 33,120. Right? So we got this 6,33,120 watts. It's nearly half. Because of half load, the input also reduced. Now we are having the output power as well as input power. From that, we can easily calculate the efficiency of the generator at the half load. So efficiency equal to output divided by input. 600 into 10 to the power 3 output divided by input is 63 lakhs 6,33,120 into 100, that is 94.76%. Right? So this is the efficiency at the half load. So in this problem, we calculated the efficiency for a full load as well as half load. During half load mean the power reduces automatically, load current, armature current all are reduced. It is nearly equal to the half of the value. Based on that, again this armature copper loss, other losses are calculated. Then we calculated the efficiency. Subscribe the channel for more videos and notification. The soft copy of this material available at the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we will see the solved problem based on the losses and efficiency of the DC generator. This part 5. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the problem. A long shunt compound generator delivers a full load current of 800 ampere at 500 voltage. The sun field resistance is 100 ohm. The magnetic and mechanical losses combined are equal to 12 kilowatt. If the full load efficiency is 92%, calculate first one armature resistance Ra, series field resistance given that Ra equal to 2 Rse, and load corresponding to the maximum efficiency. So we need to find the armature resistance and series field resistance, but the relation is given Ra equal to 2 Rse, and load corresponding to the maximum efficiency. Now we will see what are the data available. So the load current is given IL equal to 800 ampere. The terminal voltage is given 500 voltage. RSH equal to 100 ohm. The sun field resistance. The efficiency given as 92%. Magnetic and mechanical loss together is given as 12 kilowatt. That is also called as a stray loss. 12 kilowatt means 12 into 10 to the power 3 watts. Right? So these are all the given data. First we will find the output power. V into IL, terminal voltage into load current. These two data are available. So 500 into 800, the load current is 800 and the terminal voltage is 500. So that 500 into 800 we will get is 4 lakhs watts. So from this output power, already input power is given. So from this output power the efficiency is available and output power also available, so that we can calculate the input power. Efficiency equal to output power by input power. This efficiency value is given, output power also calculated. From this we can able to find the input power. So that interchange these two, so that input power equal to output power divided by the efficiency. So output power is the 4 lakhs divided by efficiency is given as 92%, so it is 0.92, right. So that we got 4,34,782 into 6087 watts. So output power always greater than the input power is always greater than the output power, right. So we are getting 4,34,782 watts as a input power. Now from this input power and output power we can easily calculate the losses, because input is given, that is converted into output and some losses will be there. So input equal to output plus losses, so that losses equal to input minus output, right. So input is 4,34,782.6087 minus 4 lakhs output. So what we got, 34,782.6087 watts is the total loss, right. So from the input power and output power the total loss is calculated. So our aim is to find the armature resistance. So before that we will find the shunt field current ISH equal to V divided by RSH. Because of long shunt the same voltage is applied across the shunt field. So the V equal to 500, RSH is given 100. So that is 500 divided by 100, it is 5 ampere. Similarly the armature current IA is nothing but sum of IL and ISH. Because of long shunt the armature current divided into the load current and shunt field current. By adding these two we can get the armature current. So 800 plus 5, right, the load current 800, armature current, the shunt field current 5 ampere. So 800 plus 5 equal to 805 ampere. So now we calculated the armature current. So from this, by using that we can go for armature resistance. So the total loss equal to, what are the total losses? Armature copper loss, shunt field copper loss, series field copper loss, magnetic and mechanical losses. So these are all the losses available, right. So the armature copper loss is IA square into RA. Shunt field copper loss is IS square into RSH. Series field copper loss is ISC square into RSC, plus this mechanical stray loss is already given 12,000, that is 12 kilowatt, that is 12 into 10 to the power 3. This total loss also we already calculated 34,782.6087, right. So that is equal to, this IA is known 805, the armature current is 805. Similarly the shunt field current is 5 ampere, the series field current is 805 ampere, right, because this IA and ISC both are same for long shunt. Now all the values are substituted, only this RA is available, so that you can easily calculate the RA, right. So RA as well as RSC, these two values are not known. So 34,782.607 equal to this 805 is taken commonly, so that RA plus RSC. These two values are simplified, that is equal to 14,500. Now this value equal to 805 square, that one relation is available, RA equal to 2 RSC, one relation is given. So that this RA is replaced by 2 RSC plus RSC into 14,500. So by adding this we will get 3 times of series resistance, 3 RSC, right. So that you can go for the further simplification. So this value is brought in the left hand side, so it is minus, that is equal to 800 square, this value into RSC, right. Now this value divided by this value will give the RSC. By simplifying the expression, we will get the series resistance 0.01043 ohm, right. So, we got the resistance of the series field is 0.01043 ohm. Already one relation is given, RA equal to 2 into RSC. So, 2 into 0.01043, that is nothing but 0.02086 ohm. So, now we calculated the armature resistance. One of the question we calculated the armature resistance. Now, we need to find the maximum power at the maximum efficiency. Now, we will calculate the constant loss. Constant loss is nothing but stray loss plus sun field copper loss, because stray loss and sun field copper loss. Stray loss is already given, mechanical and magnetic loss 12,000 kilowatt, that is 12,000 into 12 into 10 to the power 3, 12 kilowatt, right, 12 into 10 to the power 3, plus sun field copper loss ISH into RA. So, that is 5 square into 100. So, this by simplifying we got 14,500 watts, is 14,500 watts. So, the constant loss equal to 14,500 watts. So, the current at the maximum efficiency, the formula is available, square root of WC divided by RA. WC is nothing but a stray loss, constant loss, right. So, the WC value we calculated 14,500, RA also we calculated. So, 0.02086 into square root is there. So, that is nothing but 833.73 ampere, the load current at the maximum efficiency. So, this is the condition for load current. This is the formula for finding the load current and maximum efficiency. The maximum efficiency will occur at constant loss equal to variable loss. When the constant loss equal to variable loss, this at that time we are obtaining this formula. Now, we got the load current at the maximum value. From that we can find the maximum power. So, power at the maximum efficiency equal to V into IL at maximum efficiency. So, V is 500. So, IL at maximum efficiency is 833.73 ampere. So, that is nothing but 4,16,865 watts. So, it can be written as 416.865 kilowatt, right. We can write it in a kilowatt. So, in this problem we calculated the armature resistance as well as the power at the maximum efficiency. Subscribe this channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening.